All right, we are now recording, and let's just talk about a couple of things first. Let me turn the projector even. For those who were not here last time, we did get started on the first lab, okay? And in doing so, well, I'm going to use Gavin's because I don't have a spare. Okay, if you see your lab, page 359, read it, okay? Page 360, there is something to do. Number one, there, second half of page 360, bottom half of the page. If you weren't here last time, go back to the YouTube video and listen to this part of the class. I explain how to do the bottom part there. And on page 361, number 2 and 3, we do those. So you listen up on the video, and you'll be able to follow, I hope. And then at the bottom of 363, there's 4, 5, and 6, and we did all 3 of those. And then on 364, using a star chart, we found at least number 8, and I see the top 3 of number 9. Did we got all those? Huh?
We did all of them.
We did all of them. So Gavin must have left it or something and left it in here, because he doesn't have that. Okay, then number 10, we did number 10 on page 365, right? Everybody got that? Then we did what they said to do on it, and filling out table over here on page 366. We did table 47.1 at the top of the page, and if you listen on the YouTube video, you'll find me saying that second column that says SEC of the sun, that should be DEC of the sun, declination of the sun. That's on all 3 tables there. And we got all 3 tables done, right? No. First 2?
No.
First one.
We didn't get a mark on the first one.
Okay.
And then we have the last 2 to do.
Okay, that's where we ran out of time then. So what we're asked to do, and if you flip back to the previous page, you'll see it says under number 10, repeat this for December 21st and March 21st. And we got December 21st done, right? All right. So we're ready to start. This is the last third. Did I mark you here? Did you just come in? Okay, I didn't get you, I don't think. Remind me of your name. Oh, I think I did get you. Yeah, okay. Yeah, I did. When you came in, I asked. Okay. All right. All right. So we were on table 47.2. That's right. Okay, remind me. We're on 47.1, March 21st, or 47.2, March 21st? 1. 47.1, March 21st. Okay. Now. Okay. Start with this. What's the declination of the sun on March the 21st? Declination of the sun. What does declination of the sun mean, anyway? How far above or below the celestial equator the sun happens to be sitting that day. So on March 21st, where is the sun relative to our celestial equator? March 21st. That has a special name. Okay? Possibly, but okay. If you look at let's see, I know it's here we are. You turn back to page 361. Okay? That globe down there at the bottom. Okay? Figure 47.2. Okay? You see the Earth, that little ball in the middle with points at the end, those are the axes, north and south poles. And then the celestial sphere is around that, and what's parallel to the celestial sphere is the celestial equator. You know, that's just like the Earth is tilted, so is the celestial sphere. But the path that's sort of parallel there is sort of a dotted line. What does that represent? The word over here to the side is the ecliptic. The sun at any day of the year is on the ecliptic, always. Okay? And just as a little hint, the first one we did on table 47.1 was June 21st. On June 21st, the sun is here. The Earth is tilted toward the sun, and the sun is on the ecliptic here. The celestial equator is as far away from the sun as it ever is. And how far is it? Below the ecliptic of the sun. 23.5 degrees or 23 degrees, 23.5 degrees. That means the sun is way up here, whereas on the celestial equator it would be 0, so the sun is up here at 23.5 degrees north, or positive 23.5 degrees, right? And that's what you put on the first block, declination of sun, right? And then for December 21st, we're over here. Here's the sun, there's the celestial equator, where the sun is 23.5 degrees below the celestial equator, right? So that was a minus declination of the sun for December 21st. Had we done that one? December, yeah. So that was minus 23.5 degrees or 23.5 degrees south. Either way you want to phrase it. So now we're March 21st, okay? Now after December 21st, which we just had about a month ago, we're moving along here. The sun is coming closer and closer to the equator. But what happens on, what's that next little term you see there? Vernal equinox. And what's true of vernal equinox? And when is vernal equinox? March 21st. And what's true of vernal equinox? The ecliptic crosses the celestial equator. So as Thomas Earl was trying to say, it's a little above or below. It's right on it. Okay. So guess what the declination of the sun is? 0. You got it. So there's declination of the sun on March the 21st. Okay? So that's what goes in table 47.1, the third row. The second column says declination. It says second, it should be DEC of the sun, 0 degrees. Okay? Now, therefore, how many hours of daylight do you think we have on March 21st? 12. Because what do they call it here? Vernal equinox. What does equinox mean? Equal night and day. 12 hours of sunlight and 12 hours of darkness. So you can fill in the next two columns there. Number of hours of sunlight, and that's everywhere on the globe. The North Pole, the South Pole, the equator, Birmingham, Bessemer, New York City, Salt Lake City, Buenos Aires, everywhere is 12 hours of daylight, 12 hours of darkness. That's on March 21st, and that's the last two entries on table 47.2. Okay? Now let's go to 47.3. What we're doing now, see if I can find this. Readjust the globe. We're still in question 10. We don't have a globe, okay? One more time to correspond to an observer in Quito, Ecuador. And where is Quito, Ecuador? Latitude 0 degrees, which means where on the celestial equator is he?
Right.
0 degrees, sitting right on the equator. People in Quito, Ecuador are right smack dab on the equator, awfully close, and so the celestial equator is always directly overhead, okay, because they're on the equator, that's directly overhead. Now, if you're on the equator, what's the declination of the sun? Okay, wait. On June 21st. Say again? Declination of the sun. Just because you're on the equator, the declination of the sun is still, okay, quit rattling the building here, okay. Declination of the sun is always the same wherever you are. What is it on June 21st?
0.
On June 21st.
Oh.
Second, yeah, 23.5 degrees north. Same as it was in the last two tables, right? Because that's the declination of the sun. That's the sun relative to the celestial equator. 23.5 degrees north, okay, or positive, okay? Now, if you're on the equator, what does that mean about your hours of sunlight? Second? They're equal, equator, you're equidistant. So, 23 is 12 and 12, okay? In Quito, Ecuador. Okay, how about December 21st? What's the declination of the sun? South, or minus 23.5 degrees. And what's the number of daylight hours and darkness hours on December 21st? If you're on the equator, 12 and 12. And March 21st, what's the declination of the sun?
0 degrees.
0 degrees. How many hours of daylight and darkness? 12 and 12. On the equator, everything is 12 and 12. I think I told y'all before, the ones who were here last time, that I had a student in this class, this is several years ago now, who was actually from Kenya. And Kenya is another country that straddles the equator. And she said that was the hardest thing she got to get used to being here in the States, is to see that days and nights had different number of hours depending on what time of year. She said it was just so foreign to her because every day was 12 hours of light and 12 hours of darkness. Not like now, which it gets dark, what, about 4:30 or 5 o'clock, and then doesn't get light until 7 or so. And and here's Gavin. Does this look like you?
I don't think so. I'll look at it.
Huh?
I don't think so.
You don't think so? Huh?
This is mine.
Oh, I see. So leaving your labs laying around. I found it after class. It was on the floor. It must have dropped. All right. So now we're only missing Marcus and Bertram. Now I know I gave Bertram. Oh, and Derek. Did I call Derek's name before? I guess I did. Okay. And I don't have any more labs. Evidently, some people added since. Let's see if I have any more. Nope, I don't. So if any of them come in, I have to go down and run off more copies of the lab. I know I gave Bertram one because he came in. He's getting off his shift work. But Marcus wasn't here on Thursday, and neither was Derek. So if either of them come in, I've got to run off 2 more copies of the lab. I guess some people added since I made the original request. So I guess what I've got to do is use my master here. I thought I had enough. Must not have. All right, so that finishes number 10. Number 10 is all answered on tables 47, 1, 2, and 3.
We didn't do 2.
What's that?
We didn't do 2.
We didn't do what?
We skipped 47.2.
Oh, I thought I asked that question.
Oh, we skipped that.
Huh?
You went straight from the top.
Okay, well, I thought I
Table
asked
to
had we done 47.2, and I thought someone said yes. So, okay. So let's do 47.2. Okay? Sorry about that.
I put mine in the wrong.
Oh, I see. And the person answering the question. Okay. Okay, 47.2. We're, oh yeah, I remember. We didn't get to Altegard, Norway. Okay. Altegard. Norway. Okay. On June 21st, what's the declination of the sun? 23.5 degrees north, always. Now, I think I need to draw a picture for Altegard, Norway. Okay? What do they tell us about Altegard, Norway?
Latitude 70 degrees.
Aha, latitude 70 degrees. Let me get to the right page here. All right, latitude 70 degrees north. So I'm going to draw, let me get my pen set up. Okay, I'm going to draw a little globe down here. Okay, now, we're standing Altegard, Norway. 70 degrees north. It's cold there, so I have on a jacket, I mean a big heavy jacket, because it's cold there. Okay, and this is where we're standing. And if we're 70 degrees north of the celestial equator, that means the equator is somewhere here. So this is 70 degrees. Okay? That means my celestial sphere or hemisphere that we can draw here is something like that. And this is my zenith here, and the actual celestial equator probably, I don't know, that may not be enough, but this will be 70 degrees north. This is celestial equator. It parallels the equator down here, okay, or projected from that. Now, the sun on June 21st, right? That's the first one. Yeah. June 21st is, oh, and by the way, how many degrees is this? If that's 70 degrees from celestial equator to the zenith, what is it to the southern horizon? Say again? 20. So this is 20 degrees down here. So that means the sun on the 21st of June is 23.5 degrees. I'll put it the way they do in the book. 23.5 degrees north, or positive, from the celestial equator. Okay? Now, this is just pictorial. On June 21st, okay, get my globe here, my visual aid. Okay. Now, here is Norway over here in Europe, and Altegard, Norway is way up here. Here, by the way, is the Arctic Circle, which is at 66 degrees 66.5 degrees north. Altegard is up here at 70 degrees north. So on June the 21st, tell you feel like being the sun today, are you bright enough? Oh, that's not bright enough. Oh, okay, yeah, maybe so. Okay, now you're the sun, here's the celestial equator, 23.5 degrees north would be where you are. That's right there on the, what you call it? Tropic of Cancer. That's where you are. Tropic of Cancer, this little dotted line right here. So, I need to get down on your level. But Altegard, Norway is right here. Do you see it from where you're sitting? Here. You see it here. You see it there. If you see it, it sees you. So guess what? The 21st of June, Altegard, Norway, the sun never sets. In fact, that's what the Arctic Circle is. everywhere above the Arctic Circle on June 21st, because we're tilted right toward the sun, everywhere in the Arctic Circle is in line with the sun. Not a very direct line, but is in line. So therefore, the sun never sets inside the Arctic Circle on June 21st. Okay? That's as high as the sun ever gets, and it'll never set. Now, June 21st, do you see the South Pole at all? As I turn this, do you ever see the South Pole? Antarctica? No. It's all below the Antarctic Circle, so it never sees any daylight. It's dark 24 hours. So, Altegard, Norway, June 21st, how many hours of daylight? 24. How many hours of darkness? 0. Okay, let's go to December 21st. Okay, December 21st, here's the globe, pointing directly away from you, tilted away from you. Here is Altegard, Norway. Do you see it? No. Do you see it now?
Yes.
You can see it? Well, I'm not.
Yes, sir.
You see this part of Norway, but not this part, do you? Where my finger touches. So guess what? How many hours of daylight? 0. How many hours of darkness? 24. Now, the only place in the U.S. that suffers from that is the very northern part of Alaska. And actually, it's almost a third of Alaska. Here's the Arctic Circle there. Anywhere above that, anywhere close to December the 21st, 24 hours of darkness. And that sort of drives people crazy there almost. You almost have to be inside. It's frigid cold, so you don't want to be outside. You have to store up enough wood if you're burning wood, or fuel if you're burning fuel, whatever it is to keep warm, enough food to eat all that time, because there's no good hunting out there at that time. You can't raise anything out there at that time. You have to have stored it. Now, the good news is you can just leave the meat outside and it's frozen all winter. You bring it in to thaw it out. You just have to protect it from the elements and the other varmints out there to keep them from eating. But 24 hours of daylight, 24 hours of darkness. Okay, how about March 21st? Oh, did we do the declination of the sun on December 21st? What is it? Negative 23.5 degrees. It is everywhere. Okay, that's the sun below the celestial equator by 23.5 degrees on December 21st. How about on March 21st? What's the declination of the sun? 0. So how many hours of daylight? 12. How many hours of darkness?
12.
Even in Altegard, Norway, 12 and 12. Right in between the 0, 24, and 24 and 0, 12 and 12. When else will that happen?
What?
The 12 hours of daylight, 12 hours of darkness.
Where it happens?
Well,
When or where?
when? Anywhere.
Quito.
Second?
Quito. Quito. This one.
Oh, Quito. Yeah, okay, yeah. That's always there. But where else is it anywhere on the globe? When? He said March 21st.
22nd.
No. September 21st, which is the autumnal equinox. See, one equinox is here, and the other equinox is there. One of them is March 21st, and one of them is September 21st. When you're going between summer and winter, and when you're going between winter and summer. There is a midpoint both times. Okay. So that, and now I think we've got all of number 10 answered, right? Which is the 3 tables, 9 blocks in each table. You got them all, everybody? Okay. Now, this is where sometimes I mess up some, and students don't correct me. We were doing 10s from this page, but we're filling it in on this page. And sometimes I go on to 13 here. No, let's go back to number 11 at the bottom of 365. Calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees north. Okay, so we're going to have to shift a little bit here. And let me erase some of this, but not all of it. Okay. Okay, I can't quite get it all, but most of it. Okay. Calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees north. Well, if he's 40 degrees north, that means he's sitting, he or she, 40 degrees north of the equator. So there is our 40 degrees north. So this is the celestial equator. Okay? I mean, there's the actual equator. Okay? Now, the celestial equator will also be 40 degrees north. Do I have that about right? I hope so. So this is 40 degrees. Yeah. All right. Now, and there is where he is. Here's the celestial equator, he or she. Okay. Now, it says calculate the altitude of the sun in degrees over the southern horizon. Well, here's the southern horizon way over there. So how many degrees above the southern horizon is the celestial equator? When you're at, it's 50. So this is 50 degrees here. But that's the celestial equator. But where is the sun relative to the celestial equator on June 21st? You've answered it a few times.
23.5 degrees.
Which way?
North.
North. Okay. So go another 23. I probably don't have quite enough there. 23.5 degrees north of celestial equator. So there the sun is. Okay? The question is, how far is that above the southern horizon? Second? 73 and a half, exactly. 50 plus 23 and a half, you got 73 and a half degrees north. So you can either write it as 73.5 degrees north or plus 73.5 or 73 degrees 30 minutes north, however you want to say that. But that's how far it is. Okay? Got it? That's number 11. Calculation. Now do it for December 21st. Where is the sun then?
Negative.
So it's, and you're still at the same place, so now you do 23 and a half degrees south of the celestial equator. So where will it be relative to the southern horizon? What would you do here?
27.
Yeah, you subtract the 23 and a half from the 50. So that would be, I'm going to write it as, let's do it, 50.0 degrees minus 23.5 degrees, and what would that give you?
27.
Second?
27.
27, no, not 27. You borrowed one. 26.5 degrees above the southern horizon. Okay, so that's number 12. Does everybody see that? Okay. So that would be 26.5. It's ugly now because you were telling me wrong numbers. It's your fault. Okay. Okay. 26.5 degrees. Okay, above the southern horizon. Now we're ready to go to number 13 on page 366. The bottom part of the page there. Eratosthenes, who lived in the 2nd century BC, way back there, 200 years before Christ, okay, was a Renaissance man before his time. The Renaissance was way later than this, but he was what they call a Renaissance man. Here's what they mean by a Renaissance man. That means he did all sorts of stuff, did it all. He was an astronomer. He was a geographer. He was a historian. He was a mathematician. Yay, all right, okay. And a poet, okay, and didn't know it. No, I'm sorry. With such a diverse background, it's not surprising he was also director of the Great Library of Alexandria. Does anyone know where that is? Great Library of Alexandria? Alexandria what? Not Louisiana. And not even Alabama. Where are we talking about? Alexandria, Egypt. Okay? It was basically about that time, the center of learning for the whole Western world. Okay? Egypt, an ancient civilization, one of the first in this area. Now, the Chinese had a civilization, but the people in Europe didn't even know about. We had civilizations over here in the Americas. The Incas, I think, were probably pretty well civilized by them, but no one knew about them. There were probably even some tribes that were fairly civilized in the northern North America, but no one knew about it. But in Western Europe and Northern Africa, Egypt was center of learning then. Great library at Alexandria. And that's where Eratosthenes was. Now here's sort of sad news, and sad who did it too. I think it was probably during one of the Crusades. I don't know if y'all are familiar with the Crusades. Those were times when Western European kings decided they would be really great to go out and try to capture some of the Middle Eastern lands, and by that I mean Jerusalem and those kind of things, which are now controlled by Muslims, okay? And of course Egypt and most of northern Africa was Muslim as well as this. So they thought this was their divine calling to go and do that. Well, the kings were kings. Occasionally one of them went too. But mostly they sent poor old serfs and peasants, uneducated, they didn't know anything pretty much, except they had to follow orders. And they were told to go and wipe out as many of these infidels, they would have called them, maybe, or something. I'm using that term because that's what they call us now, as they could. Well, one of these times they made it into Egypt, and they decided, well, if these were all bad people, which they tended to think they were, let's burn all of their material. So they broke into the library, the great library that had the summation of all learning probably at that time, or Western Europe, and just burned at random. Whether it was Muslim stuff or Christian stuff, they couldn't read. They couldn't tell any difference. They just burned it because it was in Muslim hands. So we lost an awful lot of really valuable knowledge and information. Fortunately, the Muslims had taken that over to places like Baghdad and Babylon and places like that, and had copied much of it and hauled it there from Alexandria. So it wasn't completely lost. But that's one of the reasons, maybe, that Europe went into the Dark Ages, because there was no knowledge or information anymore. Pretty sad. And by the way, I forgot to say, India had a great civilization too. In fact, probably several great civilizations, and they had a lot of the learning there, as well as China and some other places. So, sorry for now. Okay. All right. But anyway, that's where Eratosthenes was. Before all this happened, he was at the great library of Alexandria. And one of the scrolls in the library, Eratosthenes read that at noon on June the 21st, in the southern frontier outpost of Syene, Egypt. Now, I don't think Syene is shown on here, but I'll tell you approximately where it is. It says in the southern outpost, well, here's southern Egypt down here, and Syene was somewhere down in that region, okay? Their boundaries probably weren't quite the same as they are today, okay? Near the first cataract of the Nile, okay? And here's the Nile River over here, and I take it that the first cataract was one of the first places that there was a major waterfall type thing, okay? The Nile flows northward, so it was up and coming down, and then for much of Egypt, it flows fairly flat. But way down here, you have the first cataract of the Nile. And that's about where they put the great dam, and this has been during my lifetime, the Aswan Dam. Not during your lifetime, probably, but during mine. And that probably was pretty close to that first cataract, okay? And it is listed here, even though Syene isn't listed, okay? Now, reportedly, wait. Skip the line. First cataract now. At that place, they said the obelisks. And you know what obelisks are? Anybody? Y'all know what the Washington Monument is?
They're kind of like spiders.
Yeah, it goes straight up. It's not very wide at the base or anything, but goes quite tall. Now, Egypt was most famous for the obelisk, okay? However, when they got invaded by the Roman Empire, this was quite a bit later, and it may have been then that no, I don't think it was, okay. But anyway, when they got invaded later, Rome stole a bunch of their obelisks and hauled them off to Rome. And a few of them made their way to other places like England and France too, but a lot of them wound up in Rome. And we've had the good fortune of being in Rome a few times, and you'll see the obelisks all over the city, and they're all stolen from Egypt, okay, not been returned and not planning to be returned. But anyway, these obelisks, these real tall, straight, they cast no shadows. Now, why would that be?
Because they're pointed at the top.
Yeah, well, they're pointed, but why would they cast no shadows? I mean, that tree out there could be pointed, straight up. It's not, but if it were, but it still casts a shadow. But at noon on June the 21st, they cast no shadows. That's because the sun was directly overhead at their zenith. If you looked up, the sun would have been right there. You got blinded by the sun, but don't look up there, but never look right toward the sun. Okay? As noon approached, the shadows on the temple columns grew shorter and shorter until at noon they were gone. So all the sun was directly overhead the temples. Okay? Reportedly, a reflection of the sun could be seen at the bottom of a very deep well. And normally you wouldn't see that because the sun was not directly overhead. So So on June 21st, at Syene, Egypt, the sun was directly overhead. Where would you guess the latitude of Syene to be? What would you guess that to be? On June 21st, if it was 0, that would be on the equator. Or at any time, it would be on the equator. But the sun isn't directly overhead the equator on June 21st. 90? North Pole? I don't think so. Syene, Egypt doesn't go that far. Down here somewhere. Where is the sun directly overhead on June 21st?
23.5.
Second? 23.5, exactly. And what is that line called? 23.5 degrees
Celestial
north.
equator.
The what?
Celestial equator.
Celestial equator?
No, celestial equator is directly above the equator. The dotted line.
Ecliptic.
Huh?
Ecliptic. Ecliptic.
No, the ecliptic is where the sun is at any time. And that's where on June 21st, the sun is 23.5 degrees above the celestial equator. Okay? What is that dotted line called there? I don't know if we've mentioned it yet. We should have, but we may not have. So maybe I'm asking a question I shouldn't be asking yet. That may be in the next lab. Turn back to one of these. Nope, they don't list it. Sorry, I'll give it to you. I mean, you don't need to know it. That's called the Tropic of Cancer. Exactly. Tropic of Cancer is 23.5 degrees north of the equator, and the Tropic of Capricorn is 23.5 degrees south of the equator. And the sun is directly overhead at some point between those two every day of the year. On March 21st and September 21st, directly overhead the equator, Quito and places like that, Kenya, places like that, and then the Tropic of Cancer goes just north of Havana, Cuba, through the Bahamas, doesn't quite make it up to Key West, Florida, but fairly close. So just to give you an idea, the only part of the U.S. that's south of the tropic is the nation, the state of Hawaii, and all of its islands are just south of that. So it's the only place in the U.S. that the sun will ever be directly overhead in Hawaii, and that's where it would be. So what would be its latitude? I think you said it. 23.5 degrees north. All right. Now, we're going to do one other thing here, number 14. And we don't have a celestial globe, so we're just going to have to do it on the board here. What range of declinations can stars have so that they never set? That is, they're always above the horizon. Okay? Now, that will depend on where you are. So let's take it where we are. Where do we live? What's our latitude? I've given it to you, I think, once before. Have I not? Maybe that's the next lab, too. Okay. I'll give it to you now then. Take out this one and that one. And that one. That one. Okay. I'll take away this. Now. Okay. I didn't change this any because we're pretty close to it now. We're at 33 degrees, 23 minutes, 45 seconds. Did I not give that to you before?
Yes.
Okay, I thought I did. Okay. That's where we live. So that means this angle is 33 degrees, 23 minutes, 45 seconds. Now, I don't have this drawn quite right because that's too big. So let me make an adjustment there. Okay. Something about like that. Okay. That's a little bit closer maybe. Now, and when it says what declination of stars have that they never set, you tell me what's right over here. 90 degrees from the celestial equator. You remember that? We did this early on.
Yes.
That's the may not have this quite right, but pretty close. The North Star, also called Polaris. Okay? Because that. So, the stars that never set would be all the stars that circle, because the North Star never sets. It's always 33 and a half, 33 and a half degrees. Remember, this alpha is the same as that. This is 33 degrees, 23 minutes, 45 seconds above the horizon. So basically, any star that's between here, which would also be here, okay? So 33 degrees, 23 minutes and 45 seconds. Okay? Now, what would be the declination of those stars? Well, got a little bit of figuring to do. You know that's got to be more than 33, 23, 45. And in fact, it would be exactly the difference with that and 90. If you subtract this from 90 degrees, that would be the declination of this star that never sets. It comes close, but never sets. So let's subtract that. Now I'm going to show you the easy way to subtract. You're subtracting from 90, so I'm actually going to do 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is 1 minute. Add 1 minute to 59, you got 59 minutes. 59 minutes is 1 more degree, so that would be 90. So subtract from that 33 degrees, 23 minutes, and 45 seconds. What does that leave you with? And since I have all big numbers on top, except for 1, it's pretty easy to subtract. This would be 56 degrees, 36 minutes, and 15 seconds. So any star that has a declination from the celestial equator of 56 degrees, 36 minutes, 15 seconds, up to 90 degrees. That's the North Star. That's as high as you can go. After that, it's the same declination. Okay? So there's the range. 56 degrees, 36 minutes, 15 seconds to 90 degrees. Make sense? Those stars never set. They just move around the North Star but never get below the horizon. All right, so that was number 14. Now, I don't have, it says here at the bottom of 14, your instructor will provide you with the coordinates of Mercury and Venus on the date of this lab session. I don't have that. Now, I had it a few years ago, and I'll give you this one. This is back in a few years ago, 2006. Back then, we went to Birmingham Southern Planetarium, and the lady there gave me this, so I'm going to use it from then, okay? Oh, but we don't even have the right month here. They only have September, October, November. So let's just pretend we're the same as September of 2006. No reason that we would be, but let's just pretend. So, Mercury, and it says here on number 15, when is Mercury visible on the dark sky? Okay? And basically what you can answer here, it's not. Anytime this month, Mercury is, well, let's use October. It says it's visible below Jupiter for the second half of October. So let's use that. So where would that be? Jupiter is, okay, now here's what you think of. Tell you're going to be the sun again? Okay, here's the Earth. Where is Jupiter? Closer to the sun or further from the sun? Whoa, way out there. So if it's just below Jupiter, you're only going to see that. You only see Jupiter, basically, when Jupiter is, the sun, okay. You're going to be the sun. Okay. Now, the Earth turns this way, and Mercury you can only see when it's near the sun. But Jupiter is over, here, and when will that be? Well, Jupiter being over here, then we'll only see Mercury. Okay. Stars that are closer to the sun we'll see when the sun's rising or when it's setting. Sun's further from there, it says, and they'll rise in the morning and set just before evening. Okay. But is just below Jupiter for the second half of October. This was this year. Then we see Jupiter, so we'll see Jupiter rise when in the evening and set in the morning, as opposed to Mercury and Venus will rise in the morning and set in the evening, just like the sun does. And because Jupiter is opposite, so if it's just below Jupiter, this would be just before sunset, because it's near for Jupiter. So just before sunset, number 15. Okay? When is Venus visible on this dark sky? Okay? That's going to be either just before just after sunset or just before sunrise. Well, Venus is low at dawn, so that would be just before sunrise. It'll be the morning star on those days. Morning star.
What was 15?
Second?
Yeah, was 15 told you just after sunset?
Just after sunset.
You said this before.
And 16 will be just before sunrise. Okay? Now, here's the key, the big question here. Estimate how long each is visible on in a dark sky. Okay? First, Mercury. Remember we said that. Mercury, because it just barely peaks. Period. Only time you're going to see it, I would say, a number of minutes. Not long at all. Okay? Venus, just a few hours at most. Because again, when the sun sets, Venus is going to go down shortly after. Mercury will go down just minutes after the sun. Venus, it may take a few hours, but not many hours. That's why it's called the morning star or the evening star. Number one, it's not a star at all, it's a planet. But it's the brightest object in the sky, short of the sun and the moon. The brightest thing out there is Venus. And so you only see it early morning or late evening. So it's called the morning star or the evening star because it's the first one you see. Okay? If you can see it at all. Okay. So that finishes the lab for people who were here last time. For those who weren't here last time, you'll need to watch YouTube video to catch the first part of it, the major part of it. Okay? So anytime if y'all want to, you have at least a week to complete it. Try to get it in within a week. Okay? So next Tuesday will be the deadline. If you finish it sooner, get it to me sooner. I'll be glad to take it. Okay? All right. Now, I never did actually finish all this, but I should have. We just finished Lab 1. And what's the time now? Let me clear this. Discard this. It's now 2:23. We spent more than an hour on that. All right, we're going to go until, if we can finish this chapter before 3:45, this is chapter 15 now. That was the chapter 14 lab, the lab that goes with chapter 14. If we can finish where we are now, and we were on Saturn. We were just about to start Saturn. So we've got a little over an hour and a half, or less than an hour and a half, right? A little less than an hour and a half. If we can finish this chapter in that time, then we'll do the lab for chapter 15. It's going to be tight, folks, but let's see if we can get it done. Okay? I have the lab ready, unlike last time. The copies are made, so let's see what we can do. Now, let's just go back, and for those who haven't followed the YouTube video, if you weren't here before, and you couldn't see me doing this, but you probably heard me talk about it. If the sun was here, okay, and the earth was here, then this is called 1 astronomical unit. From earth to sun, that's 1 astronomical unit, about 93 million miles, okay? Mercury was about 4/10 of the way from the sun to earth. So it was about 6/10 of 4/10 of astronomical unit from the sun. Venus was like 7/10, so that was more than 2/3 of the way between the sun and earth. There was Venus, okay, about there. Mars was 1.5 times, so half of this plus this. Mars is way out here. Then we have the asteroid belt that just is a whole big space here. And by the time you get to Jupiter, you are like 5 astronomical units. So if this was the Earth, the Sun, and that's the Earth, that's 1, 2, 3, 4, 5. There's Jupiter way out here. In between here is the asteroid belt. Well, you almost double this from the Sun, this 9.5, 9.5, I'm sorry, from 5 to 9.5, you'd almost double that, so that would be this distance, plus somewhere way over there is Saturn. Every star, planet now, is almost twice as far from the sun as the previous one. So there is an exponential increase in distances. It's not quite, but it's close to it. So it'll come back in there. 9.5 astronomical units from the sun. Okay. Now, Saturn also is the one with the most famous ring of particles. That is a picture taken from the Cassini-Huygens space probe. I believe it was built by the European Space Agency, probably with some help from the U.S. too. We participated in it, but it was mostly theirs. It took these beautiful, beautiful pictures. Okay? They're particles, dust particles, ice particles. It's a variety of particles, and they are multicolored, just absolutely fantastic. All of the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, they all have rings. None of them hold a candle to Saturn. Saturns are just spectacular. The others are just very minor little rings. These are incredible. Now here, that's one remarkable thing about Saturn. Its rings are the prettiest I've seen, any planet we know of has. Here's the next most remarkable thing. It's less dense than water. Okay? If you had a pool of water big enough, which doesn't exist, Saturn would float. It wouldn't sink. All the other planets would sink, of course. They're denser than water. Not Saturn. It's less dense than water. It's the lowest density of any planet in the solar system. Okay? Actually, less than that of water. What's the most dense planet in the solar system? Second? What did you say? Earth. Exactly. We are the densest in many ways. Okay. Planet in the solar system. And Saturn is the least dense. Okay? Now, its surface is similar to Jupiter's. Really not much of a surface. It's a really thick atmosphere. Somewhere down there you might start hitting some solid gas. It's gases that are so cold that they are frozen solid. Okay? But it's nothing like a rocky surface like the Earth has. It has approximately 30 satellites we've identified so far. Okay, and when they're satellites, these are moons. We think that Jupiter has around 50 some, Saturn has around 30 some. The rest of them, Uranus and Neptune, have maybe in the teens or something like that. We have two. We have one. Mars has two, and that's it. Okay. Now Titan is the largest of Saturn's moons, and it's the only moon with a substantial atmosphere. Most of the moons are like ours, no atmosphere. Saturn's moon Titan actually happens to have an atmosphere. Now it's bigger than our moon, but not quite as big as the two biggest moons of Jupiter. I can't remember which two they are now. Seems like it's Ganymede and Callisto, but I'm not sure on that. Those are the two largest moons in the solar system. Titan, I think, is number 3. And I was just reading or hearing something about Titan's other moon. I mean, it has 30 of them, but the next biggest moon is a pretty remarkable one itself. So I think someone may have written a paper about it or something. Yeah, from last term. I remember that was somebody wrote it from last term. 2 or 3 of the moons of Saturn they wrote about. And I had never heard of that one, and it was pretty interesting. So it's the only moon with a substantial atmosphere. Okay? Now, that's all they're saying about it. There is an illustration in the book that's not on the slide set, and I do want you to pay attention to that. These are the major rings of Saturn. There's Saturn, big planet, next in size to Jupiter, but it's still much smaller than Jupiter, but still the second largest. And then here are the major rings, but then there are other rings that are still way out there. And Titan, its moon out here, is somewhere even way beyond that. So the rings are in close, and the moons are outside of those rings. And some of them are way outside the rings. Now, do we think just because Titan has an atmosphere that there could be life there? No. Okay. Think of this. 9.5 times, almost 10 times the distance from the sun that we are. Okay? It's so cold out there. It just, no way there could be any life as we know it out there. Okay? But it has an atmosphere. It just can't support life because of the temperature. All right, so that's Saturn. Let's move to Uranus and Neptune, and unfortunately they group them together. They are almost twins. There are some differences. Uranus is the next closest, about 19 astronomical units. That's exactly twice. So if I said Saturn, okay, let's do it again. Sun, Earth. So that's 1, 2, 3. Okay. Somewhere out here was Jupiter. I think it was about here, wasn't it? Twice that far, which is beyond the wall, was Saturn. And then twice that far from there to is Uranus. I mean, it's way out there. I mean, just incredibly far. And then Neptune is not quite twice, but 30 astronomical units away. It's incredible. Now, I don't believe the strongest of our telescopes, I'm not sure, but I don't believe you can see Neptune, even with the strongest telescopes. It's only space probes that, well, that can't be true. You must be able to see it somehow because they had discovered it before we sent craft out there. But it's incredibly tiny. I mean, it's a huge planet, but it's so obscure you'd never see it with binoculars or anything else. These are the outermost giant planets. They're very similar internal structures. They have a solid core, and then a lot like Jupiter and Saturn, layers upon those, and they're just way out there. Now, this, I'm pretty sure, is Neptune. Yeah. That's Neptune. In the book, it looks a little more purplish than this. This is more bluish. But, yeah, it's out there. It's cold. It is just incredibly, incredibly, incredibly cold. Okay? It looks like there is a storm somewhere in the surface, but remember, it has probably a fairly thick atmosphere. Probably not as gaseous. Probably a lot of it is icy particulates too, because it's so stinking cold. Okay. They don't show Uranus in this slideshow. Okay. But they do in the book. And here is the weird thing about Uranus. One of the weirdest is here is its orientation. Its axis is almost perpendicular to where it should be. It spins like this, you know, as it goes around the sun. It doesn't spin like this. So whereas Venus has the weirdest spin, it actually spins backwards. Uranus' axis is perpendicular where it should be. So it spins like this. So actually in your table, the table I think has the most information about it. That's table 15.1 on page 381. It actually lists it as having a negative, just like Venus rotation period is negative 243 days. That's almost 2/3 of a year, more than 2/3 of a year. Uranus rotational period is negative 17 hours. So its tilt is such that it seems to be spinning negative. You know, if it was like this, it would be spinning negative, so it's awfully close to it. Really spinning pretty fast, only 17-hour time, and Neptune 16 hours, but going the other direction. So many things about Neptune and Uranus are very, very similar. So you can follow those. So that was the only other thing. They both have multiple moons. Like I said, maybe in the teens each, you know, something around there. We probably don't know all of them. Now, because Neptune is so stinking far out there, okay, hardly able to see it ever with the most powerful of telescopes, there is indication, believe it or not, there may still be another planet beyond that. But it's so far away we can't even see it. It's a reflection of the light from the sun such that we can't determine it, okay? And if it doubles, that would be like 60 or maybe in the 50s astronomical units away. It's incredibly far. There is enough gravitational disturbance there. We think there is another one out there, but we don't know for sure. It could be caused by something else we don't know about. All right. So anyway, there are a couple of examples here that again call on you to be able to use calculations we would have done in the first half of the book, but we haven't had the first half of the book, so you can look at those if you want to. They're sort of interesting. And that's about it. Okay, so let's move from those, the 8 planets that pretty much fit in a disk around the sun. The 4 inner ones are terrestrial, meaning rocky planets. The 4 on the outside of the asteroid belt are gas giants, much, much, much bigger. Let's move from them to smaller bodies of the solar system. Okay? Now, what these smaller bodies are, they come in several varieties. One of these is comets. Another is asteroids. We've mentioned the asteroid belt several times. And the other one is meteorites. Okay. Now, these smaller bodies are leftover material from the sun's formation and the planet's formation. This is material that really didn't get used for either one of these. So these are chunks of rock, ice, and other material, perhaps, that's just out there hanging around. Okay? And it's sort of where it hangs around and what it does as it hangs around. That's why we classify it in these three ways: comets, asteroids, and meteorites. Now, this is a statement that, if taken just at face value, you might misinterpret. It says here, the mass of the smaller bodies may be 2/3 of the total solar system mass. Now, if you took that at face value, that would say 2/3 of the total solar system mass. That would include the sun. It can't include the sun because of that statement I pointed out to you at the very first of this chapter. And that was, I'll read it to you again. This is on page 379. And I don't know if this statement shows up here in the book anywhere. Yeah, it does. It says, the total mass of all these leftovers in and around the solar system may account for as much as 2/3 of the total mass after the sun's mass is taken into account. See, the slide doesn't say that, because earlier on page 379 it said the sun has 700 times the mass of all the planets, all the moons, and all the minor members of the solar system put together. So the sun can't be included in that, because if you take everything else, add them all together, the sun's 700 times more massive than those. But excluding the sun, then the mass of these smaller bodies may be 2/3 of the whole solar system mass. That's enormous. Think how huge Jupiter is. And then the gas giants, the other four, are huge. And then the Earth and the inner four are big. And then all the moons. And then everything else. And that's about 1/3 of the total solar system mass, not counting the sun. 2/3 are in these tiny little bodies. So there's just got to be gazillions of them out there, okay? And it is. They cover an enormous area. Now, they have been detected bombarding larger objects, okay? Now, we're going to talk about comets in just a little bit. They mention one here, Comet Schumacher-Levy. Made a big mistake. It got too close to Jupiter. Jupiter has such an enormously strong gravitational field that when the comet got too close to it, it sucked it in, broke it apart, and they found, this is July 1994, there were these. And you know who saw this first? One of the national laboratories, the great somewhere, it's not anybody's way. Super telescope somewhere? No. It was a backyard astronomer, just an amateur astronomer, happened to be looking at Jupiter one night and saw these bright, shiny things here. I said, what in the world is that? I've never seen that before. So I guess the next morning he may have taken a picture of it, sent the picture to, back in 1994, I don't know how they did this, mailed it. I don't think they had internet back then. Anyway, got the information to the professional astronomers, and they said, oh, wow, look at this. And then they went out and looked and saw the same thing, probably not quite as bright as it was when he saw it. And sure enough, they determined there was a comet coming by Jupiter, awfully close about that time. Jupiter ripped it apart and sucked it in, and this is where those fragments of the comet pinged into the atmosphere of Jupiter. And as they went, they lit up because they went through the atmosphere of the high rates of speed. They burned up as they went in. It struck Jupiter, and there it is. Now, this figure in your text was back when they were talking about Jupiter. It wasn't here where they're talking about comets. they moved it around. So between those additions. Okay. Now, for the life of me, I think I have figured out where this was at some point, but I can't tell now, especially in this figure here, where that is. Let's see if I can figure it out in the book. I think it's easier to see in the book. But like I said, it's located in a different place. Yeah, it's that string in your book. It's far easier to see. Okay, where that hit the planet. Okay, so let's talk about these different classifications. Let's start with comets. Comets are classified according to where they originate, their origins. There are the long period comets, those greater than 200 years for them make one orbit around the sun. Okay? Now, they don't make orbits like we do. Ours are close to being circular, but elliptical. Their ellipses are really elliptical. Now, remember, the furthest out planet was Neptune, around 30 astronomical units out. So these comets originate the Oort cloud anywhere beyond Neptune up to a whole light year away. Remember, a light year was billions or trillions of 600 trillion miles away. I mean, it's just way out there, okay? And that's the Oort cloud. Now, the Oort cloud is basically, and when they say a cloud, it's not really in that thin plate where all the planets live. It's all around. And I think the next figure illustrates that. Okay? Now the dimensions here are hard to believe. Okay? Now that's supposed to be the sun in the center. Okay? And they don't show the inner planets at all. They just show Uranus and Neptune. Okay, those are Uranus and Neptune. Pluto is out of kilter. It's not a planet. It's a dwarf planet. Its angle is way out of where it's supposed to be, and it's very elliptical. But sometimes it's inside the orbit of Neptune, and other times it's way outside the orbit of Neptune. So it's not a planet. So, well, but all this, and this is 30 astronomical units to here. So this is about 50 or 60. I can't read that. They say that's 50. Yeah, that's about right. So that's 50. This is close to 100 astronomical units. The Oort cloud starts here. Pluto sometimes is in the Oort cloud, but it's not in that plane. It's all around. Okay? So this little bit here is right in here, okay? And then the Oort cloud starts about where that ends, that's right in there, and it goes all the way out there, one light year away. So this is 50,000 astronomical units here. Oh man, you're talking about you. So that's why they say 2/3 of the mass could be in here, because look how many objects are out there. It's just, and you see the Oort cloud, it's sort of concentrated in this disk, but it's all around that disk too. I mean, it's just everywhere. So that's the Oort cloud. Way, way out there. Now this one, I've heard it pronounced different ways. I think the best pronunciation is Keeper Belt. It looks German enough to me to be Kuiper Belt, but I've heard it pronounced Keeper Belt. I've actually heard it mispronounced pretty badly too. Okay, but I think it's called the Keeper Belt or the Kuiper Belt. It's the origin of short period comets. Those are less than 200 years. Okay, and one of the most famous of the comets, what would you say? Most famous comet you've ever heard of? Ever heard of Halley's Comet? Okay. Halley's Comet is about a 70 or 72 year cycle. So it would be from the Kuiper Belt, less than 200 years. And it's one of the more frequent ones. Now, Schumacher-Levy probably used to be about that same frequency. So they're coming from way, way away and coming in, circling, and then going back out. Okay? Not circling, ellipting, going way, way back out. Okay? Now, the Kuiper belt is in this disc-shaped region about, so it's in this disc. So I'm almost guessing that this is mostly the, well, no, that's too far out. From 30 to 100 astronomical units from the sun. So basically that would be, the Kuiper belt would be, or Keeper belt would be about from Uranus out to about there again. Okay? Because it was 30, going out to about 70 more, maybe twice that far. So it might be this little bit here would be the Keeper belt or the Kuiper belt there. And it's pretty much in the disk, okay? Disc-shaped region, 30 to 100 astronomical units from the sun, whereas the Oort cloud, that would be kind of engulf the Kuiper belt too, but it would be all this around and going out to a light year away. Now, some of these probably don't even have regular patterns by which they come into the sun, but just every now and then. And you see, if the sun is so small compared to Pluto and Neptune, I mean, so far away it hardly gets any heat at all from there, then these are way, way out there. And they're fairly small mass, so they're just held close, sort of close, a light year away. They don't go drifting off into space, but they're held around our sun very, very weakly. But every now and then one of them will make its way toward the sun and then go back out. And it takes hundreds of years, 200 years or more, for these to make a pass. Okay. The Halley's Comet, I think it was around 83, 85 or so in there the last time it made a pass by the sun. I was alive then, and you could hardly see it. I'm not sure I ever actually saw it. I think I saw it barely, a little bit. The time before when it came by, which would have been around turn of the early 1900s, it was very visible. And everybody was expecting it to be really visible the next time, and it was hardly noticeable at all. I think the time before that, it had come so close, it really lit up the sky. And people were afraid the Earth was going to end, that much. So they come various distances from, but they have little gravitational nudges that deflect the objects toward the sun, and then they come in. Those from the Kuiper belt or Keeper belt, they are a little more regular in their pattern. Okay. So that's where they come from, way out there. Their comet structure, they're small, solid objects. They don't say how small or how solid, but small. They definitely are not gaseous. They're definitely small, solid objects. One of the models is a dirty snowball. So in other words, they have frozen water, frozen carbon dioxide. Now, what do we call frozen carbon dioxide? It has a special name.
Solid ice.
Dry ice, exactly, dry ice. Frozen ammonia and frozen methane. They are so stinking cold that all these things that are normally gas, except water that's normally a liquid, they're solids, okay? Now, in addition to the frozen part of either water, carbon dioxide, ammonia, or methane, then you have some dusty and rocky bits that are embedded in the frozen material, okay? So, that's what they are, small solid objects. I'm not going to say they're all that spherical. They probably aren't. They're too small, so they're probably somewhat irregularly shaped. But there's always a head and then a tail. Okay, now not something you would flip, but a head and tail. The head is the solid nucleus, and the coma, then what you have is a surrounding bit of gas, okay? They call that the coma. It's sort of like a little atmosphere, you might think. solid nucleus in the coma. And then two types of tail. Now, one of these are ionized gases. Now, did we talk about what an ion is before? We did. It's an atom that has lost or gained electrons and therefore is charged. So it would be a gas that has been either lost or gained electrons, so it becomes charged. Or it's just dust. Okay? So those are the two types of tail, ionized gases or dust. And remember, even the comet head has dust as part of its embedded in the frozen materials. Now this is a picture of a comet, actual picture taken of a comet. Some spacecraft got close enough to it to take and magnified enough to take a picture. Now the head is around here, okay, and it's surrounded by some coma of gas, sort of like a little atmosphere around it. And then this stuff back here is either ionized gases or it's dust that's reflecting the light from the sun. Now, where is the sun? If that's the comet, where's the sun? No, it's down this way. The head is always pointed toward the sun. Always. Which direction is this going? Toward the sun? Away from the sun? What? You can't tell. Even if this is going away from the sun, the head is still pointed toward the sun and the tail is leading the way away, or when it's toward the sun. But as this goes around the sun, the tail moves like this. So the coma is always toward the sun. And if it's leaving like this. The coma is still, the head is still toward the sun, and the tail is leading the way. So it's rather bizarre, but this is either dust that's reflecting light from the sun, or it's actually ionizing gases. That ionized gases that could be producing some of their own light. But the tail always points away from the sun, no matter which way it's traveling. It could be traveling that way with the tail that way and the head this way, still going that way. Okay. Now, let me get caught up to where we are. There are a couple of examples here that, again, are asking you to do calculations based on stuff that you haven't had, so we're not going to do these. You can read through those, and I think you'll find them interesting. Okay. But let's now move to asteroids. Where do asteroids live? Okay, they're a band in the belt, in that disk, between Mars and Jupiter. Mars is the last of the terrestrial planets, okay? And then you have the asteroid belt, and then you get close to Jupiter, which is the first and biggest of the gas giants. Okay, now these asteroids have size up to 1,000 kilometers. I think this is the diameter, which would be about 600 miles. So they're not trivial. They have definite sizes. I don't think any of the comets are anywhere close to that, okay? But I don't know for sure. They have varied composition. And this probably is not too surprising, that the inner belt are mostly stony or rocky comets. Well, what are the inner planets? Those are the rocky planets. So that's not too surprising. The inner asteroids would be, the ones closest to them would be stony or rocky as well. The outer ones, this is sort of drives me a little nuts. All they say is dark with carbon. What are they? You know, they don't ever say, except they're dark with carbon. And then others, inside and outside of the others, mixed all through it, are mostly iron and nickel. Well, guess what? That's most of what the core of all the planets are. Earth's core is mostly iron and nickel. Jupiter's core is mostly iron and nickel. All of the cores are close to being iron and nickel, of what we can know and understand. Now, why are the asteroids formed? Well, they think they were formed of the original solar nebula when the sun was blowing up and, doing all of its things, before it reached a stable equilibrium. It was still sort of unstable. Things were getting thrown out and pulled in and stuff. And the comets, they feel like they were prevented from clumping together like the other planets did because Jupiter was just too close and kept ripping them apart. So they wound up being fragments out there. Whereas and what we'll look at later, all the planets fit a very regular pattern: Mercury, Venus, Mars, Jupiter, Saturn. If you put them on the right scale, it looks like you're missing a planet in there right where the asteroid belt is. And that's probably the case. Okay? So, here's sort of the picture of it. Here's the sun. Now, the scale is not anywhere close to reasonable in size here. There's the sun. Earth would be in here about right there. Okay? About the circle, 2/3 of the way from Earth to Mars, Sun to Mars would be Earth. And then about twice that far again, 4/10 of the distance from Sun to Jupiter would be the inner band of the asteroid belt, and 6/10. So right there, I mean, this is halfway between the Sun and Jupiter. Right there, right in the middle of that. Okay? This isn't quite the scale. It should be a little closer in, but just to get it to fit. And then Jupiter's out there. Now, here's a couple of my theories. I don't say this is necessarily true. Remember, Mars has 2 small moons? I bet you ripped them off the asteroid belt. Because none of the other planets in here, except Earth, has a moon. And we think the Earth's moon was formed when something collided. Maybe an asteroid, a big asteroid, may have collided with the Earth at some point and broke off part of it. This is back when we were not solid yet. And so that sort of makes sense. So I wouldn't be surprised if 2 of those little things around Mars might not have been asteroids at one time. Maybe not. Maybe it's too far away. But I almost guarantee you this. Some of Jupiter's 50 to 70 moons, I bet you it did rip off the asteroid belt. I mean, why else would it have so many? But who knows? Okay. Jupiter is a monster out there. All right, now we get to the third classification of these smaller bodies, and these are actually 3 names here: meteoroids, meteors, and meteorites. Okay? Now, meteoroids would include both of the other 2 as well. Now, remember, these comets come from way, way, way out there and come in fairly, not super close, but fairly close to the sun, swing around it, and then go way back out there, taking sometimes way more than 200 years to make a cycle. Okay? But they're getting closer to many of them getting closer to the sun than Earth is. So remember, if those are mostly icy, whether it's water ice, carbon dioxide ice, dry ice, methane ice, or ammonium ice, one of those things, ices, when they get fairly close to the sun, some of those things become gas again. Okay? And as they become gases, then they're letting loose some of that dust and dirt and particles that were held together to begin with. Okay? So when they are coming in close, they are losing some of their solid material. And those are the remnants that are left scattered throughout the solar system like trash. They're scattered there. That's what makes the meteoroids. Now that's for comets. Asteroids, the same thing, sort of. The asteroids, because of this belt, they're pretty far apart, most of them. But every now and then, they might actually collide with each other. And one of them gains some potential kinetic energy and some loses. With that one that lost, if that collision was strong enough and hard enough, it may be broken, and some of those pieces start falling toward the sun. Well, those would be what now are called meteoroids. They at one time were pieces of comets or pieces of asteroids, now they are meteoroids. It's just space trash out there. Okay. Now, when does it become a meteor? That's when it enters the Earth's atmosphere. Okay? When a meteoroid actually gets close enough to the Earth sucks it in, just like Jupiter sucked in Schumacher-Levy comet, sucks it toward it, and it enters our atmosphere. It's going at a pretty high rate of speed to begin with, and we're moving at a high rate of speed, so it collides with our atmosphere. Even though our outer atmosphere is pretty low density, it's still interacting with gas molecules at high speeds. Friction burns it up, okay? And that's what you see. What do we call that? When you see them burning up, coming through the atmosphere? Two names. So,
Falling stone.
yeah, what?
Falling stone.
Falling stars, sometimes called shooting stars. Those two, I couldn't hear which one you said. Meteors are shooting stars or falling stars. When that meteoroid happens to come into the Earth's atmosphere and starts to burn up, we see it there, and that's when it becomes a meteor. Okay. Now, what they call meteor showers, that's when the Earth passes through where one of the comets is gone, the tail, what's left over, and you pass through all this extra dust and dirt there, then we pass through and we get hit by more of them. Okay, that's what's called a meteor shower. We're going to see a table on that later. Well, what is a meteorite? Well, all meteors were one time meteoroids just floating around out there. They're meteors when they enter the Earth's atmosphere. Well, if that meteor burns up in the Earth's atmosphere, that's all it was a meteor. It burns up. But some of them are big enough and hard enough that when they enter the Earth's atmosphere, it burns all the way but actually lands on the Earth. That's when it becomes a meteorite. A meteoroid that survived the meteor stage, a falling star or a shooting star, and actually hits the Earth's surface. Now, there are three kinds of meteorites that have landed on the Earth. One is an iron meteorite, and remember we said some of those asteroids out there are mostly iron and nickel. So that could be a leftover from one of those asteroids. Or they're stony. Well, that could be from the inner bunch of asteroids or any of the comets, because they had some in it. Now, the stony have two types, chondrites and achondrites. Well, what in the world is that? Well, let's start with a chondrite. Chondrite, the solid pieces are somewhat spherical in shape. Now, and those are called achondrites. Those are called chondrites. Those spherical shapes are called chondrules, if you want to get really complicated here. Before we hit this, let me hit a figure 1518 in your text. It didn't make the slideshow. Is a close-up photo of an asteroid. You see it's pitted because it's been hit many times by other space junk. And it talks about three craters that are near each other that have been named the Snowman. That's just little stuff. Missed mistakes and misunderstanding. Now this is good. The asteroid belts. Astronomers have cataloged hundreds of thousands of asteroids. These are Greek for starlight, but they're not anywhere close to a star. I'll let you read that. It's pretty interesting. The asteroid belt is nowhere close like these chunks of rock are. They are far, far, far apart. Space is a huge place. All right, now let's get back to the chondrites and achondrites. I'm going to read this to you. The stony meteorites, that's the middle category, further subdivided in two groups according to their structure. The chondrites, the achondrites. Chondrites have structures of small spherical lumps of silicate minerals or glass, and those are called chondrules. So that's why they're called chondrites, held together with a fine-grained cement. The achondrites do not have the chondrules, so that means they're not chondrites. Okay, but they have a homogeneous texture more like volcanic rocks, such as basalt that cooled from molten rock. So, the chondrites, more of a siliceous material. We'll talk about this 2 chapters from now. Silica-type materials. Now, have any of you ever been around the furnaces where they make steel and that kind of stuff? Sometimes what's left over from burning of coal or other materials that have a variety of things in them, the solid materials, the burning is so hot that it all either vaporizes or melts anyway. And then when they cool, they form little spheres, sphere-like things. And that's often called, I think, slag. Are y'all familiar with that at all? A few people I've had in classes before actually either knew someone, their fathers or uncles or somebody who worked in the steel mills, and they sort of know a little bit of what I'm talking about. When a solid material either melts or even vaporizes and then cools again, they form little spherical particles, especially the glassy particles like silica. Those would be the chondrules. Those that don't, they are more like the iron-based materials, like the salts, that when they harden, they don't harden back as chondrules. They don't make little balls. Okay. So those are the stony kinds. They're either silica-like or non-silica-like. And then you have the stony iron, which is a mixture between the two. Okay. So those are all classifications of the leftover junk that's just hanging around the solar system. And when the Earth passes through them, the meteoroids, or when they're out there, if they hit the Earth's atmosphere, they become meteors. If they make it all the way to the surface, they become meteorites. Most meteors burn up completely in the atmosphere. Okay. How are we doing time-wise? Well, we got 30 minutes, don't we? Because we'll go till 3:45. Yeah, that's right. Okay, we might make it. Now, here are some of these meteor showers. And we just missed one of the sort of bigger ones. January 3rd was the Quantrid, which you had about a meteor every 2 minutes. Okay, 30 meteors an hour. The next one coming up is in Aquarius. It's called Aquarid, and that's May 4th. That'll be after this class is over with. That's only one every 12 minutes. I'm not sure. I mean, May is pleasant weather. You might sit out there, because that's on a weekend, and just look at the sky for a while, see if you see any meteors. It has to be a pretty clear night to tell. One of the more prolific ones coming up in August, Perseid. This is somewhere in the constellation Perseus. About one every minute and a half. Okay, about 40 per minute, per hour. Okay, about one every minute and a half. So that was about one every minute. Okay, Orion is. I know where Orion is. That's my favorite constellation. I can pick it out. And on October 22nd, and that's about one every 4 minutes. And then Taurids, that's in Taurus the bull, which I never can pick out, or Leonid the lion, I can't ever pick out. These are around November, but they're only like once every 12 minutes, so I'm not going to stay up in a whole night looking for that. But the biggest one is Geminid, and that's in the constellation Gemini, which I don't know, I can't ever pick that out either. December 12th, almost one a minute. But it has to be a fairly clear night for you to see it. That's the most prolific of our meteor showers. So we really don't have anything much coming up anytime soon. Sorry about that. But they happen just about every year because we go around the sun and we pass back through that comet's trail once a year, so that's when we hit the meteor showers. All right. And here are some illustrations of these types of meteors. And this to me seems totally backwards. The first one here, I think they call a stony meteorite. Okay? It looks really dark. The next one is an iron meteorite, which is much lighter. And in the next chapter, or 2 chapters away, we're going to learn iron forms really dark material, and stone, siliceous material, is light colored. Well, these look totally backwards to me, but they treated the iron meteorite with acid and made it look really light. So that's the difference. But that's still awfully dark for a stony meteorite to me. Okay. And then the other part of figure 1519 in the book is a time lapse that shows these various during a meteor shower, and you see how long they kept the aperture open. I don't know, but you can see there were quite a few meteors that night. They don't look all that big, and you have to really be watching and careful to see them. Now that doesn't show up on this slide. All right, now we're ready for the origin of the solar system. This is 15.3, which is the last section in the book, but it is several pages, so let's see if we can get covered here. So, here's a model. We think this is what happened. Okay? It's called the protoplanet nebular model. Nebula meaning, again, a cloud of gases that are sort of pulled together. In stage A, this is the formation of the heavy elements in many earlier stars and supernova. Okay? Now, this is a solar system, so the sun's being formed at the same time that we are. And that's this picture here. Something has made the material sort of clump or group together, a gravitational nudge, something like that, some sort of a phase, and this is stage A. And if you remember back when you have a star falling apart, it doesn't fall apart, it explodes apart, and when that happens, many of the heavier elements are formed. Well, those are the things that will clump together first to get things started, and that's what's probably at the core of the sun, but it's also in this band that goes around the sun. Okay? And this is way early in the sun's formation. This is the proto-star. The sun isn't a star yet, but it's going to become one. And the planets are not planets yet. Okay? They're just clouds of gases formation. That's stage A. Concentration in one region of space as dust, gas, and chemical compounds. There's most of it centered around the sun, but then a bit of it scattered around a disk around the sun. And there's other stuff out here too, and that will later be the Oort cloud of comets. Okay, so there's stage A. Stage B, that's this one. The formation of a large rotating nebula. Okay, the sun has sort of settled in and is becoming a star now. Maybe not totally, but pretty much there. But what was out here, still gaseous. Well, the sun's still gaseous. It's still really hot. And this is still gassy and floating around there. They're not really formed yet. You have the gravitational contraction. The spin rates are increasing. Most of the mass is concentrated in the central protostar, so it's not a star yet, but getting there. The remaining material forms what they call the accretion disk. So all this cloud that was here before is settling out into pretty much of a disk here. And different parts of the disk are grouping together. The remaining material, the material in the accretion disk begins clumping in groups. So if these were the 4 inner planets, then that would be Mercury, that would be Venus, this would be Earth, and that would be Mars. Or it could be that the inner planets are in here. These are Jupiter, Saturn, Uranus and Neptune, or something like that. But whatever it is, these are still gassy. They're not solid yet. Okay? Just like the sun's not a star yet, it's still a protostar. But they begin grouping together. Now, let's say that there were the three smaller rings in here, and then you had another one out here. It could be that Jupiter is just preventing that next ring from ever clumping. It keeps them separated. And if they stay separated too long, then they're probably not ever going to group together. They group together as smaller bodies. Okay. So that's the B part. Stage C, that's the bottom one here, the protostar becomes a star. Okay? Okay? I don't know why they didn't say the protostar becomes the sun. That would have made more sense. It finally has settled out. The solar ignition flare-up may have blown away the hydrogen and helium from atmospheres of the inner planets. Because remember, Mercury has basically no atmosphere at all. Venus has a very dense atmosphere, but not much hydrogen and helium. It's mostly carbon dioxide, sulfuric acid, those kind of gases. We have mostly a nitrogen atmosphere with some oxygen in it, but that's mostly provided by the green plants. And then Mars has a very, very thin atmosphere. The asteroids have basically no atmosphere, and then the hydrogen and helium that really came from the sun when it was blowing up and doing things like that, those lighter gases got pushed all the way out to the gas giants, and they accumulated in those places. Okay? Now, the solar ignition flare-ups may have blown away the hydrogen and helium. Okay? The protoplanets heated up, separating the heavy and the light minerals. The heavy minerals concentrating in the cores, the lighter minerals near the surface. The larger bodies cooled slower, with the heavy material settling out over longer times in the central cores, and slowly the other parts, they may have cooled faster because they weren't as inner more. So we went through sort of a strange formation stage there, going from gaseous clouds sort of clumped together to actually being solidifying and being planets. Okay. So here are some ideas about the solar system. Way back, you can understand this sort of if you think about it. If you are watching the bodies in space, you know that the sun rises in the east, goes up, and sets in the west. It looks like it's moving across the sky. And if you go out at night, the stars rise from the east and set in the west. Okay? The planets do some weird things, but you don't see them that much anyway. The moon rises in the east and sets in the west, but it has a very different rhythm and pattern to it than the stars and the sun. Okay? So guess what? Everybody thought the Earth was the center of the universe. And the sun was going around the Earth. The stars were going around the Earth. The moon was going around the Earth. They got that right. Okay? Sorry. Even the planets kind of were going around the Earth. Okay? So the early Greek astronomers and philosophers tried to explain those observed motions of the sun, moon, and stars. They put the Earth in the middle and the others going around. They originally had circular orbits of them. They didn't fit too well, so they started monkeying around with things. They just couldn't get the planets to work right. Because, and we'll see a little bit later, Mars, for instance, will be rising in the east, and night after night it seems to be moving a little like this, and then all of a sudden it'll stop and start moving this way, and then it'll turn and start going back this way again. Not in one night, but over several weeks and months. It says, hey, what's going on here? It backed up on itself and then went back again. None of the stars do that. The sun certainly doesn't do that. The moon doesn't do that. It's just these planets. And actually, the name for planet means wanderer, because they sometimes lose track of what they're doing and seem to wander off and then get back in line. So these strange activities, things that weren't circular in pattern and stuff, they were trying to be explained by, he was a Egyptian, seemed like he was one of the big leaders, but I think he may have just been a great scientist named Ptolemy. I know that's the name of, I think, one of the pharaohs or something like that. May have been Ptolemy too. I don't know if it's the same one, but anyway, he tried to explain it away. And he got it to work fairly well, but it was really a convoluted, complicated model. And over time, it didn't work well either. For a short period of time, it did. Well, inconsistencies of this system grew in number as time went on, and it became more and more complicated to try to get it to work. Okay? Now, much of the evidence seemed to be that things went around the sun. They don't. I mean, around the earth. They don't. That was the whole problem here. But many of the thinking of it, unfortunately, the Christian church was not a good player here. There was some type of place, I don't even know where in the scriptures it is, that suggests that the earth was the center of something. I can't even think what it is. But anyway, that got into their mindset that we were the center of everything. Well, like teenagers, right? Never mind, say that. Okay. But that we are the center of things. And that began to be the teachings. Well, when somebody came up with a model, and that somebody was a guy named Copernicus, which is sort of interesting because he himself was a monk. He was under the auspices of the Roman Catholic Church. But he was discovering things using telescopes and stuff and modeling things, but he wasn't publishing. But the word got out through other scientists that were also doing the same thing. Copernicus has a really interesting model here, you know, and stuff. Galileo, perhaps the greatest scientist of his time, looked into this, read up on it, looked through his improved telescope, said, you know, I think this guy's right. Well, Copernicus lived somewhere up in Poland or somewhere, way away from Rome, so he could sort of get away with it. Poor old Galileo lived in Pisa, Italy, which was not that far from Rome. And when he came out and said this, he, the greatest scientist of his age, the church could not handle that. Some of them actually wanted to execute him for spouting these beliefs because they were not based on the same thing they wanted to believe. Others said, hey, you really can't go around executing someone with his credentials, but we'll put him under house arrest. So he was for years under house arrest. And he was forced to recant everything he had said. But then he wrote privately, they made me recant this, I really don't. You know, but that wasn't published until after he died. Okay. So anyway, church was not a good player here. They forced people to try to believe this, but after a while, you just couldn't deny it any longer. Okay? The idea of the earth revolving around the sun was from Copernicus about 1543, and then later came Galileo and then Kepler. Okay? So, here was what the problems were before. If you really put the sun at the center of our solar system, with the earth going around the sun, here we are observing Mars, and Mars is way out here. Well, Mars doesn't go as fast as the earth does. It has a lot further to go. And if on these months or whatever, there's some time period, if at this time period you look out at Mars, there it is. And over here you look at Mars, and there it is. Well, it seems to be following a pretty regular path. Here, it's there. Hey, that's not too far up. But then when you get here, it's over here. Whoa! Well, that's because the earth is rotating, revolving this way, it's revolving that way. Somebody went and jumped. It really jumped fast here. Well, Well, then at 5 is here, so it slowed down again. And 6 is here, it slowed even more. 7 here, but it's doing pretty regularly. Oh, wait. Sorry about that. This is where it appears. This is the actual location, I'm sorry. That's where it appears in the sky. So there it is, there it is, there it is. Oh, that's pretty regular, following along. 4 speeds up, sort of, but not too bad. But then, look at 5. It was over here, and actually goes here in between, and then comes back to here. Mars, what are you doing? You're not following the pattern everything else does. 6 is over here again, okay? But then 7 is, here's Earth, there's, ooh, it got off here. But somehow, that's where it is, and then it goes back to being a very regular pattern again. But in between there, it sort of got lost. It just started wandering around, and then went back to a regular pattern. Well, that's all because of this. If you model this after Copernicus's model, it all makes sense. But that has the sun at the center, not the Earth. Now, what convinced Galileo was he could see through his telescope that Jupiter was spinning. You could see that the sun was spinning. Hey, if all these other things are spinning, why wouldn't the Earth spin? And if they're spinning, that's what makes it look like the sun and the stars are going around it. But they're fixed in space. It all makes sense. Except to the church at the time. Okay. So you could explain with the heliocentric model. Now there was still a little bit of a problem. Even these models had the orbit of the Earth and the orbit of Mars being circular. And they just aren't. They're slightly elliptical. That's where Kepler came into play. And he said if you make these orbits not circles but ellipses, not far from being circles, but just slight ellipses, that would further explain the heliocentric model to T. Very, very good fit here of the data. Now, and we'll study most of that other later. We'll get to that. Oh, we did do it. We finished chapter 15 within the allotted time. So there it is. Now, in your book, and I wish they had shown these, so I'm going to back up. That's the last figure they showed. This is a gross exaggeration of Kepler's model. Okay? And when I say gross, I mean really gross. He has the sun here, the other focus here. There isn't really anything there. Here's a planet going around. There's not a planet out there that has this elliptical of a model. Usually these two foci are much closer together, almost on top of each other, just not quite. But he did it. They did the illustration here for a purpose. So the first of the models says that first law states that each planet moves in an orbit in the shape of an ellipse. Not that big of an ellipse, but an ellipse. Foci are much closer together. But every one of them is like that. And even the Earth going around, the moon going around the Earth, it's elliptical. That's why Sunday night? Wasn't it Sunday night? I believe it was. It was such a big looking moon because then the moon was closest that it ever is to the Earth, very close to that. And that's why it was so big, okay, and why it fell completely within the Earth's shadow for so long, probably close to an hour, or maybe close to 2 hours, okay, because it was that close to the Earth. So that's the first law. The second law states an imaginary line between the sun and the planet over a given time period is going to sweep out an equal area. Now that doesn't look like it's equal, but this is so small this way, this is so large this way, this is wide this way, that's narrow, but the areas are the same. That's the second law. Now the third law is this one, and this is sort of complicated. The square of the periods of the planet's orbit is proportional to the cube of the planet's semi-major axis. That would be the one that goes this way. What? Well, here's what it turns out to be. If you plot these on what they call a log-log scale, plot the planets, and you see on the log scale, each unit here is a power of 10. So 1 and 10, you know, from 0 to 1 is the same as 1 to 10, and that's the same as 10 to 100. That's a log scale. You log scale this way and a log scale that way. Look at these planets. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. If there was another one in there, that would be the asteroid belt. If that were a planet, it would fit perfectly. They go straight line on a log-log scale. Okay? And they're evenly spaced. Whereas in reality, every one's almost twice as far as the previous one, so they're an exponential spacing. So that's illustration of Kepler's third law. You don't need to know these, just that Kepler came up with these three laws. And there was a guy that came before him named Tycho Brahe, or Brahe, something like that, that put together a mathematical model, but it's strictly empirical, and it worked for a certain length of time. But Newton came along then. Meantime, Galileo constructed his telescope, added observational support to heliocentric, and then Newton came along and was able to give basis for Kepler's laws, scientific basis. And there are examples here that use some of the calculations, again, that you would hit in the first half of the book that we aren't doing here. Now, like I said, most chapters have a person behind the science. The one for this chapter is Gerard Peter, and again, I don't know how to pronounce his last name. I believe some people say Keeper, and to me it looks more like Kuiper, but I don't know how it was pronounced. Okay? But he's the one. He was Dutch born, so he was born in the Netherlands, but he came to the U.S. and did his work as a U.S. astronomer. And so the Kuiper belt was named after him, or Keeper belt, whatever you want to call it. Now, this little blurb cannot be your source for a paper. This can give you ideas for that, but you'll need to go outside the book to get your sources. So, if you want to choose him, he's certainly a good one to look at. You might find other people named here that might be good, or other ideas here. So I'll let you look at that. They talk about several of Neptune's moons. So if you want to do a paper on Neptune's moons, that would be interesting. Okay? But anyway, here's that. I say this every chapter, and I mean it every chapter. All that I say, all the PowerPoints, everything else, doesn't hold the candle to reading the chapter. And really a good idea to read the chapter first before I talk about it, then it'll make more sense. Okay? Even if when you're reading it, you say, I'm not following this, read it. And then when I talk about it, the synapses in your brain kind of start clicking together. It could be that when I'm talking about it, if you haven't read it, it sounds like I'm going blah, 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 and it's not making any sense. And then when you go back and read it, and oh, okay, maybe that does make some sense. So it's a lot better to read it first and then hear it. But it's better to read. Once you've read, then things like the summary hit some of the high points a little stronger. So take a look at that. Key terms are listed here. About normal, I guess, the number for most chapters. Applying the concepts, 41 multiple choice questions, maybe a few fewer than most, but still way more than you'll have on your test. They have the answers here. Now, these questions won't show up per se on the test, but the same material they're asking about will be covered on the test. So that's the best thing to study for the test. 19 questions for thought, that's probably a few more than normal. 6 for further analysis, that's about normal, maybe 1 extra. More on the conversations between Earth and other celestial bodies. They seem to like to go into that. And then there's parallel exercises that are more like the examples given in the text. You almost need to know the first half of the book before you can work on those, but if you want to look at some of those, you certainly can. Any questions? Chapter 15. All right. What we'll do in about, I was going to say in about 5 or 10 minutes, but I looked at my watch wrong before. It is almost that time now. So do you feel like you need a break? At least get up and stretch, restroom break, potty break, bladder break, whatever you want to call it. Or just move around, get something to eat or drink, whatever, wake up, whatever. If you want to do that, let's keep it less than 5 minutes. And when we come back, I'll call roll the second time. I'll pass out your labs for chapter 15, and then we'll do the lab for 15. Hopefully it won't be quite as long as the lab for 14 was. It's a fairly long lab, but I think it'll go more quickly. And then hopefully we'll get it done in the 2 hours, maybe even finish a little early. And if so, you all get to leave a little early. But don't bank on it. Okay. But that means we finish this chapter. So the last 30 minutes on Thursday, we'll have the test from chapter 15. Now, many of you opted not to take the test on 14 because you had just entered the class, and that's understandable. But try to get that made up before we get to, well, if you can, before the test of 15, which is Thursday. If not, as soon as you can. Let me tell you again my office hours, okay? Tomorrow, I have office, well, number one, if we finish a little early tonight, you want to take the test then, that's a great time to do it. If you aren't ready tonight, then office hours on tomorrow, 8 to 10. That's the best chunk of office hours I have tomorrow. After that, there's just little bits and pieces because the last part of tomorrow I drive to the Birmingham East Campus and teach a physics class there from 4:30 to 6:30. So I just don't have any other chunk of office hours except my lunch hour, which is 45 minutes tomorrow, and that's about 11:45 to 12:30. You can catch me then if you want to. Friday, I'll be on the Birmingham West Campus, and I'll be there from 8 to 12, actually till 12:30, because we have a meeting at 12:30. So if that's a good time for you, hey, I'll be there. But you have to tell me you're coming, otherwise I won't have your test with me. So if you are going to take it Friday, let me know. This is the Chapter 14 test. But the Chapter 15 test will be the last 30 minutes of Thursday's class. Now, what we'll do, the first part is Chapter 16. Now, how far we get, I don't know. If we do Chapter 16 in an hour, 2.5 hours, 2 hours, if we can get it done in 2 hours, then we have time for the lab for Chapter 16, which basically isn't that long of a lab because the rest of the lab you are going to be doing at home, okay, over the next couple of weeks. But if we can't finish that chapter in 2 hours, then we'll finish the chapter and get started on Chapter 17 and then back up and do the lab the next day. So we'll just keep it going like that. If we can finish the chapter in 2 hours, we'll have the Chapter 16 chapter, 2-hour lab on 16. Actually, we can get it done in less than 2 hours, so we may go a little over stuff, and then have the test the last 30 minutes from Chapter 15. And then we'll have the test for 16 the next time, if we finish it next. Yeah. So we'll just keep going that way. I don't ever want to give you the test the same day we finish. I want you to be able to digest it and study it after we've talked about it. Does that make sense? Okay, why don't you take a quick break. Try to keep it less than 15 minutes. I will shut down the PowerPoint here. I'll pause this. And this. Okay. Now, this is talking about motions of the sun, which is loosely associated with the chapter we just finished, Chapter 15. this has some information at the beginning. Let's talk about the formal definition of what noon is. Noon is 12 o'clock. Every day at 12 o'clock is noon. Technically, noon is, remember, if you face due north and draw a line from due north directly overhead, your zenith, down to due south, that is your local meridian, and your noon is when the sun crosses that meridian. That's the highest point it will be at any time of the day. Now being in January, it's not very high. It's a little higher every day, not much, just a little bit, but that's the highest it will be all day long when it crosses your meridian. That's called when it transits. And that's technically what noon is. And it varies from day to day. It's not always 12 o'clock. And that's what this lab is going to be talking about. Now, what we call a solar day is when it crosses your meridian one day to when it crosses the meridian the next day. That's one solar day. But if you think about Earth's motion in space, that's a little strange because you see, we are spinning around our axis once a day, but we're also transiting around the sun. 1/365th of the way around the sun every day. So we spin, but we also move around the sun, so by the time the sun crosses our local meridian, it's not one spin. It's one spin plus a little time because we've also moved a little ways. Okay? So, rather bizarre. Okay? If we had picked a star, any old star, that's usually up, and said when it crosses our meridian, now the North Star, we don't choose that because it's always on our meridian. It never crosses it. Okay? But any other star, when it crosses our meridian, we can pick one over here too. In fact, it'd probably be better to pick one of these because these never set. And measure from when it crosses our meridian one day to the next day. We're not going around that star. That's different from a solar day. That's called a sidereal day, meaning around a star. Sidereal somehow means stars. Okay. Getting a little ahead of myself. There are two parts of a day. Okay. Ante, which means before or pre-meridian, that's AM. Ante-meridian, before meridian. After meridian is called post-meridian, PM. So that's why the hours up before noon are called AM hours, and the hours after noon are called PM hours. After post-meridian, before the cross of meridian, after the meridian. Of course, on the other end of it is midnight. Of course, there's no sun out there then, so you don't see it. So anything after midnight is AM, and before midnight is post-meridian PM. Okay. Post-meridian means after the meridian. Okay. And before the meridian is ante. So don't think the A is after. It's not. It's ante, which means before. And post means after. Okay. Now, they do a little bit here about how the Romans did their days, and they were really strange. They said every day was 12 hours, no matter how much daylight and sunshine you had, so their hours had to vary in lengths. In the summer, the hours were long, and in the winters, the hours were short because they made it be 12 hours of daylight. Really bizarre, okay? So that was strange. I don't know why they even went into that. It's not scientific at all. Okay, so the first procedure is going to talk about the difference between the solar day and the sidereal day. This day based on the sun crossing our meridian as opposed to some star crossing our meridian. The time it takes between those two. Well, the Earth spinning on the axis, that's part of both of those. But because the stars are out there fixed in space, that would be exactly one spin of our axis. A sidereal day. Exactly one spin of our axis. About our axis. A solar day, though, has both the spin and the movement around the sun, revolution around the sun, so it's a little bit longer, just a little bit longer. Okay? So, the first question here is on page 371 of this lab I just handed out today. And that says the sun moves 360 degrees around the ecliptic. Okay, let me get my pen set up here. Remember, the ecliptic is where the sun is at any given time. So it's 360 degrees around that ecliptic in 365 days, 1 year. Actually, 365 and a quarter approximately, okay? So that's almost 1 degree a day, right? Approximately 1 degree per day, okay? Now, therefore, the sun is about 1 degrees east. Now, they're saying, let's take day 1 to be the vernal equinox, where the sun's ecliptic crosses the celestial equator. Right there, that day, that'll be day 0. 1 day later, okay, the sun has moved a little way. So it's moved on the ecliptic, but the equator is still the same place it was. So 1 sidereal day later would be 1 spin of our axis, but now the sun has also moved a slight distance, about 1 degree. So how long is it going to take to move that 1 degree? That's the question. Okay? Now, and they're referring to the figures here, and you've got the lab, so I'll let you look at the figures. It's on the next page. This is day 0, vernal equinox, okay? The next day, the sun has moved a little bit along the ecliptic, 1 degree more, approximately, along the ecliptic, but when it crosses the celestial equator, the spin, that would be 1 spin right there, but the sun's gone a little bit longer. Now the question is, how much longer? Okay? So, here is how that breaks down. 1 degree is how many minutes? 60 minutes. And 60 minutes in a day, and how long is a day in hours? 24 hours. Wait. No, I'm sorry. That's not what I want. Okay, sorry. That's true, but that's not the ratio we're after. Okay. So that 60 minutes is a day. Now that's 1/360th of the time around the revolution around the sun. Okay. Now, and that takes revolution around the sun is wow. Usually when I hear this, I think the automotive students have just gotten out of class because their cars almost always sound like that. So I always stop. I teach them in the fall, and when they would leave here, give them a few minutes, I'd hear that every time. So never mind. Okay. Okay. It's basically the same problem we had last time. The picture here isn't particularly great, but it gives you the general idea. Okay, so here's what you do, I think, okay. 24 hours is 1 day. Let's get that in minutes. No, that's not right either. Oh, no, okay, that's it. It takes 24 hours to move 1 degree, okay? And, yeah, 24 hours to move 1 degree. We don't need the 60 minutes, okay? 1 degree. What is this ratio? Oh, that's not right either. It's okay. Basically, 360 degrees in 24 hours. Okay. That's how long, okay. One time around, one spin is 360 degrees, and it takes 24 hours to do so. So how many hours does it take to do one, or what fraction of that does it take to do 1 degree? So let's see. Divide that, and what do you get? 360 divided by 24. Okay, that's 15 degrees per hour. Okay, we remember we did this before. Okay, now we want 1 degree. Okay, well, that hour is 24 minutes. 60 minutes, I'm sorry. 1 hour is 60 minutes. Okay. To do 15 degrees. So how many minutes would it do to be 1 degree? Someone may have said it. 60 divided by 15. 4 minutes per degree. That's what we wanted to get to. How many minutes does it take to move that 1 degree? And that would be 4 minutes. So a solar day is approximately 4 minutes longer than the sidereal day, the day based on the stars. And that's what we were getting at here. That's number 1. Okay? Express your answer in minutes, 4 minutes to move that 1 degree. Okay? Now, question number 2 that you see on the bottom of page 371 is referring to figure 48.3. Nice picture, and this really is what we mean by the signs of the zodiac, for those people who follow horoscopes and stuff like that. It's when the sun is entering the different things in different times of the year. The earth is at different positions, so the constellations on the opposite side of the sun change over the year. As the earth moves around the sun, then the constellations we see that the sun's eclipsing is changing over the year. Okay, that's what it's talking about here. Figure 48.3 depicts the sun's apparent motion along the ecliptic, where the zodiacal, however you say that, constellations are found, in a heliocentric perspective, as the Earth orbits around the line of sight of the sun toward the background stars also move. For example, the sun shows, the diagram shows the sun in Leo, because you're here on Earth, the sun appears to be in the constellation Leo. I can never pick out a line from Leo, but they drew one here. Okay. A month later, it will have moved on to Virgo. And Virgo is the one next to Leo because the Earth moves a little bit further. 1 month later, it's in Virgo. And I don't see what that is either. Okay. But anyway, so that Virgo lies behind the sun. Can anyone find a question there? I can't. So number 2 has no question, so it has no answer. So don't worry about number 2. So that's how the constellations work, by the way. Okay? Now, that was part A, solar and sidereal day. And then, on page 373, we have part A, the analemma. Okay? Wait, how many part A's are there? I don't know. I think this is supposed to be part B. Okay? Because this is the last. We won't have the part C. So this should be part B, the analemma. The tails of the sun's motion. Now, we're going to talk about the analemma more in the next chapter. Okay? So we're getting introduced to it here, but it's going to show up again in the next chapter. Okay? Chapter 16. We just finished 15. Okay? Now, what the analemma is, and by the way, that word means the same as sundial. Now, there's 2 types of a sundial. There's one that has the thing sticking up in the shadow of the sun, marks what hour it is. And the Romans use that. That's one way. This one, though, is a different one, and this is sort of an annual sundial. And what this is this shape, and you'll sometimes see it on a globe. My globe here doesn't have it on it, but some globes do. Other times you'll see it, like when we were in Trieste, Italy, with visiting friends of ours, there was one on the side of a building. This figure 8 was like this, though, and that was their analemma, okay? Now, we could actually, if y'all hung around long enough and wanted to do it, we could do our own analemma. Okay? Somewhere, maybe not in here. But if we covered every window with black plastic, and at the middle of the day, at noon, middle of the day, and we cut one little hole in the black plastic so the sun came through there and formed a spot on the floor, and every day of the year we mark that spot. We move the desk out of the way and mark the spot where the sun shone. That day, we would mark the analemma. We would have a little figure 8 looking pattern there on the floor. That indicates where the analemma is. Now that's when the sun was crossing our local meridian. So it would have to be that noon, not noon by the clock, that noon, and we could mark it, and there would be our analemma. So this is what we call the analemma, figure 8 that marks the transit of the sun over an entire year. Okay. Now, a couple of features of this analemma. Notice what it goes up to. The side, what you might call the y-axis here, the vertical axis on the side here, is the declination of the sun. And what are the ranges of that? From declination of the sun?
0 degrees.
Okay, at the equator it's 0 degrees, and when is it at 0 degrees? Right around
15th.
September the
25th.
not 17th.
25th.
Second
25th.
20. Yeah, it's a little before the 25th. See, the 25th is right there. That'd be the 23rd, around the 22nd, 23rd. Or go on over, and when is that? March the 21st. Guess what those dates are?
The summer solstice, winter solstice.
The autumnal and vernal equinox, exactly. Sun's up 12 hours, sets for 12 hours, okay? So what does it go up to? What's the maximum, the declination of the sun? And when is it? First, what is it?
23.5.
23.5 degrees. And when is that?
June 21st,
Right around June 21st, which is called
the summer solstice.
summer solstice. And when is the minimum? And where is it? December 21st, right down there. And what is that called?
Winter.
Winter solstice, exactly. Okay? And notice up before the summer solstice, the declination is getting just ever so slightly greater, and then stops and starts getting less. And right around December 21st, on days before that, it was getting lower and lower, but not very, very much. And then finally it starts going up again. So you see it was very gradual, sun standing still here, the sun standing still there. That's what solstice means. So yeah, this tells us about our tilt of the earth. Okay? That's part of it. Okay? And that's what they're talking about on the next page, page 375. The spin of the axis is 23.5 degrees, blah, blah, blah. Now, another reason that it's odd shaped like this is that when you go back to Kepler's laws, the sun is here. At some time we're close to the sun, other times we're further away from the sun. When we're closer to the sun, we move faster. When we're further away from the sun, we move more slowly. That's part of being an elliptical orbit. And because of that, that makes part of the analemma fat and part of it thin. Because when we're moving, believe it or not, we're farthest from the sun, believe it or not, in June and closer to the sun in January. Okay? So we're moving faster in January, slower, so it gets off a little bit more easily down here. So all sorts of weird things are happening here. The analemma covers it all. Okay? Johannes Kepler talked about the planet moves fastest at its perihelion, that's the point closest to the sun, slowest at the aphelion, which is the point furthest from the sun. Okay? And the perihelion is January 3rd, we just had it, and the aphelion is on July 7th, and that's still coming up. Okay? So, we'll talk about that more next chapter. Okay? So this analemma graphs the sun's declination, that's on the vertical scale, the daily difference between clock noon and noon of the sun, or the sun on the meridian, for every day of the year. Okay? So let's take a look at that. This is top of page 376. Looking at the figure 4.3, which is the analemma, they got this pump. That should be 48.4. I don't know where the 4.3 came from. 48.4, okay? We see the sun is west of mean sun, that is ahead of clock noon from December 1st to December 26th. Here's December 26th, and September, there it is. September 1st to December 25th or something, 26th. We're ahead of clock noon because your time is here. So here we're ahead of clock noon. When you're over there, you're behind clock noon. Okay? Now, question number 3. Here we finally get our second question. Briefly describe the effect of the shape of the analemma if the ecliptic equator angle were to increase. What is the ecliptic equator angle now? Ecliptic equator angle. Maximum angle, that differs. Second?
Declination.
Okay. What is the amount? Maximum amount? 23.5 degrees. Well, what if that were to increase? That's what the question was. What would have to happen to analemma? It would have to stretch vertically. So that's number 3. It would have to stretch vertically. Okay? All you have to put. Briefly describe the effect of the shape of the analemma. If the ecliptic equator angle were to increase, that would stretch it vertically. Probably not change anything horizontally, but stretch it vertically. Okay? Now it says, obtain from your instructor the latitude of our location and fill it in below. And I've given you this before. Here it is. 33 degrees, 23 minutes, 45 seconds. Now that's here in Bessemer, approximately where we are. Okay? That's not exact, but it's pretty close. Okay? It's not Birmingham, it's Bessemer, this part of Bessemer here. Now, the second part of 4 says, determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Okay? Now, I think what I'm going to have to do here is erase what's on here. Sorry, I wish I hadn't written that number on there. I'll write it again. Okay. Here is the globe. We are standing right here. Okay. The celestial equator is 33, not celestial equator, the equator. Here's the equator. We are 33 degrees, 23 minutes, and 45 seconds north of our celestial equator. There's our horizon. Here's the northern horizon. Here's the southern horizon. Here is our meridian, our local meridian, going from north to south directly overhead. Directly overhead is called our zenith. Okay? Here we are standing right here in Bessemer, Alabama. Okay, at that. So the celestial equator is about right there. And that is 33 degrees, 23 minutes, 45 seconds below us. You know, that's from our zenith down there. Okay? Mirroring what this is. Those are equal angles. So the question is, the altitude over the southern horizon, which is right down here, okay, of the local celestial, of the celestial equator, which is right here. Here's the celestial equator. So what is that distance? How do we get it? Second? Subtract it from 90. Perfect. Except I don't want to use 90. Guess what I'm going to use? 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is 1 minute. That would make it 60 minutes. 60 minutes is 1 degree. That would make it 90. So subtract from this 33 degrees, 23 minutes, 45 seconds. And what do you get there? 36 minutes, 15 seconds. 56 degrees, 36 minutes, and 15 seconds. That would be this angle right there. Okay? Got it? Now, says use the analemma. This time they gave it the right thing. Figure 48.4. They got it right this time. And your answer in step 4 to fill in the table below. That's 48.1. In your thing it said 47.1, and I corrected that to be 48.1. The latitude of Altegard, Norway, which we'll do on the second part, is 70 degrees. So we'll come back and do that. We'll first do this. So first, declination of the sun on the 15th of February. Was the declination of the sun on the 15th of February?
14 degrees.
Is it? Or is it 13?
13.5.
Say again?
13 degrees.
13 degrees south, or minus 13, right? Because it's south of the equator. Okay? So that's what goes in that first blank there. Now, that's the declination of the sun 13 degrees below the celestial equator. So I'm going to draw it right there and say that's about 13 degrees. Okay? So what is the noon altitude of the sun when you're here in Bessemer? We figured this was 56, 36, 15 to the celestial equator. This is 13 degrees below that, so what would we do? Anybody? Say again? Subtract 13 from this. 13 degrees even, that would be 43 degrees, 36 minutes, and 15 seconds. So that's what goes in the middle column by February the 15th. We'll come back and do AltaGuard next. Let's go down to June the 21st. Okay? First ask for declination of the sun, June 21st.
23.5.
Oh, yeah, we didn't even have to look that up, did we? That's 23.5 degrees, or 25, yeah, 23.5 degrees, 23.5 degrees, whatever you want to call it. Positive, negative, north, south, what?
Positive.
Positive, very good. What's the noon altitude of the sun at that, when we're at our location? So there we're 20, ooh, goodness, that was weird. This is drawing, there we go. That's probably not right, but here's 23 degrees, 30 minutes. Okay? So what do we have to do to get the altitude of the sun then? What's that?
The first, February 15th.
Yeah, add it to our 56. So do the 56 degrees, 36 minutes, 15 seconds, and add to that 23 degrees, 30 minutes, and 0 seconds. Okay? So the 15 seconds comes down. I can add that. 30 and 36 add to what? 66, but that's more than that's 66 minutes. So that would be 6 minutes, add 1 degree, carry 1 degree. Okay? And then this would be what? 80. 80 degrees, 6 minutes, 15 seconds. So at noon, where we live, we're awfully close to directly overhead, but we're not. We're a little less than 10 degrees short of that. Awfully close to directly overhead. That's why our summers are so hot. Okay? So there's June 21st. Let's do October 15th. What's the declination of the sun?
8 degrees south.
8 degrees south. So 8 degrees south would be somewhere around in here. So we subtract 8 degrees from the 56. So I'm just going to erase part of this. Whoa, I erased my horizon too. Shame on me. 8 degrees from 56, and what would that be? 48 degrees, 36 minutes, and 15 seconds. Everybody see that? You subtract 8 rather than 13. Okay? And then, got to get on the right page here. On December 22nd, what is the declination of the sun?
It's about the same as.
Yeah, it's about. But and what's that?
It's negative 23.
Okay, so then you subtract this, and that would be somewhere like this. So subtract that from this. So here, let's do the subtraction. Do you mind if I do it this way? Because it's so much easier. Subtracting 23 degrees, 30 minutes. The 15 seconds comes down. What happens here? 6 minutes. Second? 33. 33 degrees, 6 minutes. So basically only about a third of the way up in the sky. At noon on near Christmas Day, or 22nd of December, the sun doesn't get any higher than about a third of the way up. Summertime, summer solstice, it's almost at overhead. 10 degrees sort of overhead. This time it's only about a third of the way up. Okay? Now, let's do the same thing for Altegard, Norway. So let me erase as much as I can here with a, ooh, that didn't pick up, did it? Okay. This will actually be a little bit easier just because we don't have any minutes and seconds in it. It's just going to be degrees. Okay. Yuck. I'm losing everything here. All right. I may be old, but I'm slow. Okay. All right. See if I can draw. Ooh, that's a lousy looking globe, isn't it? Okay. Earth. Now, 70 degrees at Altegard, Norway. Here, I put on a jacket here. Okay. And here we go. Here we have 70 degrees from the equator, which means 70 degrees here from the equator. Whoops, 70 degrees. Which means what do we have left? Here's the celestial equator. That's what? 20 degrees. Okay, so that's our setup when we're at Altegard, Norway. Now, guess what? Declination of the sun didn't change any. Exactly what it was before, but I've already erased mine. What was it?
For February, it was -13.
Okay, negative 14?
13.
13. So 13 degrees south of that, which means what's the altitude of the sun then? Don't tell me you're using a calculator for that. 20 minus 13? 7 degrees. So there we have 7 degrees. This angle here, if this is 13 here, this would be 7 degrees. Now mine's not to scale, obviously, but you know, anyway. Okay, what's the noon altitude? What's the declination of the sun on June 21st? 23 and a half, 23:30.
7 south or north?
Second?
7 degrees south or north?
Okay, altitude above the horizon is always above the horizon. Okay, so it's above the horizon. See, south of the celestial equator, but above the horizon. Okay. Now, so if this angle is 23 and a half degrees, what will be the declination of the sun? I mean, not declination, the altitude of the sun then? Second? Yeah, 43 and a half degrees. Perfect. Or 43 degrees, 30 minutes. Okay? Everybody see that? You add 23 and a half to 20 and you get 43 and a half. Okay? So that's June 21st. October 15th, what was the declination of the sun? Second?
-8. -8.
-8.
Negative 8. Okay, sorry about that. My hearing's so bad. So this time, we're only dropping 8 degrees, not 13. 8 degrees, so what does that leave us here then? 12. So the sun gets up to a whopping 12 degrees above the horizon on October 15th at Altegard, Norway. How about December 22nd? What's the declination of the sun?
-20.5.
Okay, minus 23 and a half, but this is 20, so what is the noon altitude of the sun? It isn't! That sun's below the horizon. Well, guess what? On December the 22nd, you're north of the Arctic Circle, sun never comes up. So you can either put a -3.5 degrees, or you could just put never rises. That's what I think I'd put, because it doesn't have an altitude. It never rises on December 22nd. Make sense? All right. Oh, this is a little bizarre here, but I'm going to have to erase everything again. So let me go through and erase. Okay. Okay, let me see if I can draw my circle a little bit better. I can't draw it any better. Sorry about that. All right, Rip Van Winkle, of course this is legend, it's not true, awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. The passerby quickly responds and then rapidly moves away. Now, if I had been sleeping, if anyone had been sleeping about 20 years, I have a feeling why he would pass by pretty quickly, okay? Rain, shine, whatever, this had to have been pretty right by then. Okay, and also looking pretty ragged too. Realizing a 20-year snooze might be a world's record, he thinks he should pin down the date as well as the year. So he just woke up now. He has no clue what day it is, okay? It's been 20 years. He moves out from under the tree where he slept and measures the altitude of the sun as it crosses the meridian. Pretty sharp dude, huh? Crosses the meridian. He finds it is 44 degrees over the southern horizon. So 44 degrees would be something like that. 44 degrees. There's the sun on the day he wakes up. Now, obviously I bumped something and it didn't go too well. 44 degrees, okay? He knows that the latitude of his chosen spot on the Hudson River is 42 degrees. So that means this angle right here is 42 degrees, which means that this angle right here is 42 degrees, okay? So what, and that means this is the celestial equator. So what does that place the declination of the sun to be? Okay? Second? Okay, 44 and 42 would add up to be 86, and what's left there? 4. So this would be 4 degrees south of the celestial equator. That's the declination of the sun on that day. So we turn to our good old analemma back here and find out what 2 days the sun will be 4 degrees south of the celestial equator. That looks like about what?
October.
The what?
October 6 or 7.
No, you're going the wrong way.
The 4th.
The 4th. Okay, October 4th, or
Yeah, and March. March 8. I mean, 12. Something.
yeah, 11th or 12th. You pick the day you think that's closer to. So it's either October 4th or March 11th or 12th, whichever one you think is closer to. Okay? Now, he doesn't know which of these, except, so that answers the first thing. On what 2 possible dates could Rip Van Winkle have awakened? Okay? Write those 2. Then he notices that the buds are appearing on the tree he slept under. So what date is this probably? March 11th or 12th, whichever you chose. Okay, we got that one done. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. as an example, check the analemma, and again, they put the figure wrong, 48.4. They put 4.3. I guess that's what they had back on the other one that was so messed up. I don't know. They must have changed labs and rearranged it. I don't know. To see on October the 15th, okay, so go back here and look at October 15th. You see it there? Now, you have to use a horizontal scale, and this is the one at the top. So take that one that you see there, October 15th, go all the way to the top, and you see your 14 minutes to the left, and that's before clock noon. They tell you that, 14 minutes before clock noon. So anything to the left here is before clock noon, anything to the right is after clock noon. Okay? Now, for the dates given in the table below, use the analemma. This time they got it right. No, they didn't quite. It's 48.4. They got 48.3, but they're getting closer. To determine whether the actual sun will cross the meridian before or after clock noon, and by how many minutes. So the first blank there, that middle column, all you write is before or after. No numbers, either before or after. In the right-hand blank, that's where you'll put the amount of time, and that will be in minutes. Okay? So let's do January 10th. January 10th.
After.
It's after. So in the first blank, you put after. Now you figure out how many minutes.
7.
Say again?
I don't know. Hang on.
Take the line from January 10th.
7.
Yes, it looks like 7 minutes after clock noon. You see that, everybody? Y'all see how we're getting this? Okay? Or should I be asking each individual person? Okay. February 15th.
After.
After, how many?
14.
Yep, 14 minutes. You got it. April 15th. Tax day! We want our favorite, okay?
2 days after my birthday.
Is your birthday? Oh, wow.
2 days after.
Oh, 2 days after. Okay.
After.
After? About how long? Now this is a little tough here.
1 minute.
Say again?
1 minute.
Okay, April 15th. Now you see, April 15th starts to the right, and then April 10th is closer to clock noon, and April 15th is it's after, but it really looks less than 1 minute, doesn't it? You see, 10th is after clock noon, 15th is after, but less than a minute after, and then 20 would be before clock noon. You see it?
Yeah.
So
Between 0 and 1.
I'd say less than 1. Amount of time before. You already put after, and let's say less than 1 minute. Okay? April 15th. So you can't say, oh, I had the taxes in on time, but you see, you have to take into account the time check. No, you can't do it. It's right on the money. Okay, July 30th.
After.
Oh boy, there's after again. Okay? How much after?
6.5 minutes.
Yeah, about 6.5 minutes. If you want to say 6, that's close enough. 6 or 6.5 minutes after. Okay? Bunch of afters here. How about September 1st?
Before. Wait.
I think it's after as well.
Yeah, there's the 5th, 4th, 3rd, 2nd. Yeah, looks like it's after. And again, less than a minute. Okay, or 0. You can put that if you want to. How about October 30th?
Before.
Before. If October 15th was before, you're pretty sure that this is before. Also, the 30th, how many?
6.
16 minutes before. Very good. Everybody see that? Okay. Flip one more page. We're almost there, folks. Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian on the dates in the table below. So what we got to do is go back to our local meridian. So I've got to erase some stuff here. How are we doing on time? Okay? All right, we're doing well.
It's only 4:50.
Yeah, we got plenty of time. We could stretch this one out, couldn't we?
No.
No?
No, it's not.
Oh, man. Okay. Okay. Wait, one more thing here. All right. Now this one, I haven't really changed much here. So I'm going to call this 33 degrees, 23 minutes, 45 seconds. Okay? So therefore I don't know if that's right, but it's approximate. 33 degrees, 23 minutes, 45 seconds. And we want the altitude of sun over the southern horizon. So what is this one again? Do we need to go back and do it? Any of you still have it? This angle here then. We did this earlier.
Oh yeah.
Oh yeah.
It's like the 56.
56
30,
degrees,
36,
36 minutes,
15.
and 15 seconds. Okay, that's what we're starting from. Okay. So, sun altitude. On May 15th, what can we get off the analemma? May 15th.
It's before.
Okay, we aren't quite there yet. Let's first do the altitude of the sun. What do we use here? Say again?
I will use the declination.
Yeah, we'll use the declination. What's the declination of the sun on May 15th?
19.
About 19 degrees, and that's
North.
north, so it's added to that. So we'll do this as 19 degrees. So add 19 to this, and what do you get?
75.
75 degrees, 36 minutes, 15 seconds. Right? So there's your first blank after May 15th, altitude of the sun. Now the time when it crosses the meridian. You said it was before clock noon. How much before?
4. Wait, yeah. 4 minutes?
4 minutes. So what time would that be? Before clock noon.
Oh, 11:56.
11:56 a.m. Anti-meridian, before it crosses the meridian. Anti-before. Okay? That was May 15th. June 15th. Is what?
It's right at.
Yeah, like 23.5 something.
It's not quite 23.5 yet. Let's call it 23. Okay?
23.
So add 23 to this rather than 56. Adding rather than 19, we'll add 23. Oops, I didn't erase. $23. That would be what?
79.
79 degrees, 36 minutes, and 15 seconds. That will be the altitude of the sun, and what will be its time when it crosses the meridian at June 15th.
12.
Ooh, 12 o'clock noon. Right on noontime. Okay, very good. So I usually write that 12 o'clock noon because I never know whether to put PM or AM. So I just write noon. So no confusion. Okay? Next, November 4th.
15.
15 what?
15 south.
South. 15 degrees south of, this is our celestial meridian. I should have, celestial equator, sorry about that. Okay, and this is 15 degrees south. So that's minus 15. So this time we subtract 15 degrees from that. And what does that give us?
41.
Okay. 41 degrees. 36 minutes and 15 seconds. That's the altitude of the sun on November 4th. And what time?
17.
So again?
It's about 15-ish minutes.
About 15 minutes
So,
before clock noon, so that would be
11:45.
11:45. That sounds reasonable. 11:45 a.m. Anti-meridian before it crossed the meridian. How about December 25th, Christmas Day? What's the?
24 degrees negative.
I don't think it gets to 24. Do you?
23.5.
Yeah, I'd say 23.5 because it can't get any more than 23.5. So we'll subtract 23.5, and that's negative. So this is down here somewhere. Minus 23 degrees 30 minutes. That's 0.5. Okay, so subtract that.
32.5.
Okay, really quick here. Okay, but I would do 30 minutes because we got minutes up here. 23 degrees 30 minutes. And that'll be what?
33.
33 degrees 6 minutes and 15 seconds. Okay, and what time?
It looks like it's about a minute before noon.
Actually less than a minute because that line would be a minute and you're just, actually it's just a few seconds before noon.
11:59.
Huh?
11:59.
And 35 seconds. I don't know. I mean, I'm happy with 12 noon. But if you want to do something else, you can. That's fine. I'll count them both. Okay? Does that make sense? Got it? Not quite as long as last one, right? Okay.
No, that
I
was
don't.
a little short.
What's that?
That one was a little shorter.
Yeah. Now, we should have been doing each individual person, shouldn't we? Yeah. Okay.
Yeah, that's
All right. Any questions? Okay. So, next time, we'll start the day, chapter 16. We'll go for at least 2 hours. Okay? And if we finish 16 in 2 hours, then we'll do the lab for 16, or at least start it. Even if we're a little bit more than 2 hours, I think we can get everything done in the lab at a shorter time because part of the lab you do on your own. So we'll see how it goes. But then the last 30 minutes will be the test from chapter 15.
Okay.
All right, good deal. And remember, on the test, what can you bring? Formula equation sheet. Anything you want to write down on a piece of paper, front and back, you can do. Ready to turn it in? Good deal. Thank you. All right, good deal. Oh, you turn in both of them.
We don't write here anything, right?
What's that?
Here,
What is this?
we don't have to write anything here, right?
No, just number 7 is down here. All right,
This
good
is
deal.
just, this is for
Goodness,
chapter
all
one.
this grading. Oh,
Chapter
man.
1.
Okay.
This is both of them.
All right, thank you. Goodness, I'll be grading forever.
Can I go tomorrow at your lunch thing on 14 6?
Okay, that's between 11:45 and 12:30. Okay, yeah.
Okay.
You know where my office is?
It's down.
256, yeah. 265, I'm sorry, 265.
So I wrote my research paper. Can you
Okay.
guess the topic?
What's that?
Can you guess the topic?
Can I get the copy?
Guess.
Yes.
The
Oh, the topic? On the one in here?
Yes.
Okay. Probably not.
Creation of universe.
What's that?
Creation of the universe.
Oh, okay. Good deal.
I wrote 7 pages.
Oh, 7 pages? Wow.
It's creation of universe.
Yeah, it takes a while to create the universe, doesn't it? Okay.
But the
It only took
information,
7 days.
Yeah. 1 page a day? Yeah. Okay.
the information I put is so amazing.
Is what?
The information
Yeah.
I wrote
Yeah.
is the accurate information.
Is what?
It's 100% accurate.
Oh, it is. Oh, you were there, huh? Okay.
Yeah.
All right.
I just need to print it off.
Oh, I see. Okay. And did you get the one for the math class too?
I will do it.
Still working on that. Okay. Good deal. Well, that's the one I remember you telling me you were going to get done.
And I have books if you want to like see.
What's that? You have a book, what? All right. We'll see you Thursday.
Oh, tomorrow?
Oh, yeah, you're going to come tomorrow? Yeah, okay, I'll see you tomorrow then. Uh-huh.
And this book is read by famous, it's like Henry David Thoreau,
Oh, wow.
Ralph Waldo Emerson,
Uh-huh.
Albert Einstein,
Uh-huh.
Beatles, and is also like by the State University of New York
Uh-huh.
and all.
Just what? Oh, okay.
Is like this gives knowledge about both gross and subtle part of living beings.
Of what?
Subtle part of
Yeah.
living beings.
Oh, of living beings.
Gross and
Right.
subtle.
Yeah, I got it. Okay.
So this is so much knowledgeable.
Wow. Yeah.
You want to read it?
I got a bunch of books for my birthday, so I'm still reading on those. It'll be a while before I ever get to them. I was not a fast reader, so
I mean, at least you can like keep it or just.
that's all right.
Yeah, you know.
It's fine. It'd probably take me so long you'd be gone before I ever finished.
Yeah, I know, but you can. This is not one-time book.
Yeah.
This is full of knowledge.
Yeah. Okay.
Yeah.
Well, I'll remember the titles, I think. So if I, get to the end of my reading list, then I'll head
But
on
the
that.
author it should be this.
Yeah. I saw that one, but this one was
The same author.
same author. Okay.
Yeah.
And both of these are from well back in the past.
No, like this talks about science.
About what?
Science.
Science. Yeah.
Yes.
Yeah, but this was back Henry David Thoreau before they came along.
Yeah,
Ralph Waldo Emerson. So that
Yeah,
would have
like
been back.
this knowledge is like this book knowledge contains
Right.
from time immemorial.
Yeah. Right. But
Knowledge in this book.
right.
Yeah.
But he wrote it in about the
No.
1700s.
Like knowledge like is given in the beginning of the
Right. I understand
creation.
that, but it was the copyright, so to
Yeah.
speak, was in the 1700s or 1800s, something like that.
Yeah.
Yeah. Right. Because.
But this is like new edition.
Yeah.
He like wrote it in in 1900s.
Yeah. Right.
Like
Yeah.
this is like modern English language.
Right. Yeah. So because
It's nothing related to any religion.
right.
No religion in it.
Right. Okay.
It talks about science.
Right.
So you are a science teacher, so I thought you will read.
Oh. Okay.
But this is so good.
Yeah.
And
Okay.
knowledge is so good.
All right. Super. I look forward to reading your paper.
Yeah, like sometimes when you are teaching the chapters,
Uh-huh.
like we have doubts, right? Like who created and how it works.
Right.
All this in this.
In there. Okay.
Or
In that one. Yeah.
Yeah. So
All right.
it's so nice book.
Yeah. So I'll look forward to reading your paper.
Yes.
Yeah, because you took it from those two sources, right?
Yeah, and some web,
Yeah. Okay.
internet.
Yeah.
Compare with the Big Bang Theory.
Yeah.
Comparison.
Right.
Yeah.
Do they compare favorably?
Huh?
Do they compare favorably?
You will read it.
Okay. I'll look forward to it.